Okay, I think we can start. What time is it? 9:29. Okay. So the first thing that we want to show you is, as I said before, is a couple of concepts from Python itself, not a package or anything, that that one has to do with the memory management of Python, which are reference counting and garbage collection. And in the second one has to do with multi-threading in Python. That is the global interpreter lock, or GIL. That yeah, probably we have heard about it. And so before that, for many people, Python sounds like something that it shouldn't be on high performance computing, because Python itself can be slow, and in general, when we hear HPC, we think about C, and Fortran. But in practice, there are many options to do numerical things with Python, and every day I think that there are new stuff. And I think this is in part because well, Python is well liked. Everybody likes Python, and something in particular that is very good in Python to develop software is that many functionalities in Python can be redefined, and you can adjust very easy Python to the way you want your package or your program to work. For instance, on Thursday we're going to see Dask, and in Dask we're going to see that doing something like z equal x plus y won't mean sum x plus y. It will mean create a graph where z that x and y is going to be sum, and it's going to give z, sorry. And after that, you can add more pieces to the graph in the same way you would do sums in Python, and then later you can execute the whole thing. And so this is something that is very convenient of Python. And another point is that Python is very easy to glue to other languages that are used in HPC, like C, C++, and Fortran. And in fact, the kind of Python code that we're going to be seeing in this course, and is in general used for numerical calculations, it looks something like this. So if this is the execution time of a Python script, these codes in general, they have a main Python thread that we will call some code like C, for instance, and this code will do some heavy calculations. And then when this code finishes, it returns, and the Python program continues, and we'll call other kind of C code. And this C code can create multiple threads, or can access the GPU and so on. And because of this, at the end we are using Python, so we have the good thing of Python, like this main point. But in the back end, we are doing calculations like we would be doing in traditional HPC with C, C++, and Fortran. Okay, and so this is something we want to say. And okay, so the first point, the reference counting and garbage collection. So this is, as I said before, this is related to the memory management of Python. And memory management is complicated. This has many rules, and it's not easy to predict what is going to happen with the memory, but at least it's important to know how it works, at least in a big overview, so we can have in mind things when we are writing our code. So here, this is going to be an example to try to illustrate how these two things work. So the memory management in Python. So let's say that you have a script, it's a Python script, and it starts by creating a random number. And then you say A equal np random. or size m. So this is going to allocate a block of memory in the in the Python memory, and a mechanism in Python that is called reference counting is going to assign to this block of memory a number that is called reference, that it will be equal to the number of variables that are pointing to this block of memory. So there are references in this block of memory. So in this case that we have only a, the reference is going to be 1. So if the script continues, so there is this operation b equal a transpose. This is an operation that we will see later that doesn't need to create new memory. So then b is going to be pointing to the same memory, and now Python is going to increase the reference of this block of memory to 2. Okay, and this is how it's going to happen for every object. So if we have more objects, we will have something like this. So this one will have reference 2, and this 2 will have reference 1. And now let's say that we delete C. So we do del C. This one automatically, when you do this, the reference counting is going to be set to 0, because now nothing is, no variable is pointing to the memory, to this block of memory. And this is not only because we deleted the variables. If we do something like this, C equal 1 or C equals something else, now this C is going to be pointing to where the 1 is stored in memory, and this block of memory still won't have any reference to it. So it's going to have reference 0. And when this happens, so there is another mechanism that goes in like cycling over the execution time of your Python script. That's called garbage collection. And when the garbage collector sees a reference, a memory block with the reference 0, it will mark it as free for Python. And now Python can use this memory again. Okay, but something important is, if in the script it continues and it creates a new array that with n equal m, so we need it will need a bigger memory block to store this e. It won't fit here, and in NumPy there is no such a thing like putting part of the array here and part of the array here. So this memory block that it was used before is just going to be it's just going to stay there empty, and it will be only used if new memory is allocated that fits in this array. So in this case, the next step of the script was f equal something like this, the same size, or if it is smaller. And this is like this, the memory can be reused. And of course, so this is a very high level. This is not the rule or anything at all, but understanding at least at this level how the memory is managed in Python, it can really help you to organize your code and think how the memory is going to be affected with every line of code that you do. Like things like, for instance, in this case, that there are cases that there are operations that do not create new memory, and in like this case, that the C, we got rid of it, but other things in the script will have to use new memory even if there is empty memory. Okay, so this is the first part. The second part is the global interpreter lock, or GIL, in CPython. CPython is an implementation of Python. It's the most common implementation of Python that people use. So a global interpreter lock is a lock. It's a concept in computer science, and a lock is exactly what is written here. Is a mechanism for enforcing limits when accessing resources in an environment where there are many threads of execution. So, and in Python there is a lock, and Python is written, the code itself is written in such a way that when there are multiple threads, so if you have a script that creates multiple threads in Python, and the code is pure Python, when the first thread that starts running is going to lock out the other threads, so this only thread can run, and the rest of the threads are blocked, and they have to wait until this thread finishes executing or finishes a part of the execution, and it will allow the other ones to run. And when the other ones are allowed to run, the first one that starts will lock the other ones out, so this one can run. And in pure Python code, something that is multi-threaded will run in multiple threads, but not in parallel. So they will run one after the other one, okay? And a nice way to understand this is through an analogy with, there is an example that it is a game that kids play, and the game is to tell a story, and a bunch of kids they tell the same story, but they tell parts of the story. But now, so not to avoid that all the kids talk at the same time, so you can see the kids as the threads, and the problem, the story, telling the story. So to avoid that all the kids talk at the same time, the teacher that is with the kids give them a toy, give to one a toy. So there is one toy, and the kid that has this toy is allowed to talk, and another kid cannot talk unless this kid gives them the toy. And now this kid that doesn't have the toy anymore cannot talk. And like that, the whole story can be told by multiple kids and multiple threads, but not in parallel, so they cannot do it at the same time. And in logs, when talking about logs, there are two terms that are used, that are releasing the log and acquiring the log. So in this case, the log would be like the toy. When a kid acquires the toy, which is the log, it can talk, so it can execute. Well, he or her, not it, sorry. And when it passes the toy, that's why it releases the toy, and someone else acquires it, now that kid can talk, and so on. And the same thing happens in Python. Python itself is written with all the functionalities you can imagine. Like every functionality of Python will be wrapped by this thing. And when something will start, it will acquire the log, it will lock everybody else, and when it finishes, or when it finishes part of what it's doing, it will execute a release, and it will let the other threads to run. Okay, and we have here an example to, oops. Yeah, we have an example here to see that. So this one, I will show it to you as a demo, but you have it in the repository, so you can later you can play with it if you want. So we will be using a Python threading module to simulate how Python works. And we're going to do the following. We have these two functions, function 1 and function 2, that they do two silly things. So there is an internal loop here that loops over hello from the first function, and it will print each of the words forming the sentence, but one by one. And between every print, there is here a time to make it slower to show the point that we want to show. And this one is going to print everything in red, and this one is going to print the same thing, but it's a second function, but in red. So we have these two functions, and we are going to run them in two threads, right? So we have thread 1 and thread 2. So one is running the function 1, and one is running the function 2. So we start the threads, and we finish them, okay? And we see that here we are running this multi-threaded thing. So this is forcing the multi-threading to make what we want, just to show what happens in when there are no logs, no. So here, if we run, so the two threads will be running at the same time. At the same time, no, they will be running at the same time, but not in parallel. It will be one after the other one, because it's still Python code. but one thread is going to be interrupting the next thread. So you see the mix of green and red. Okay, so this is what we wanted, to see something like this, because that's why we did the for loop, because if we put directly print the whole thing, so the print is going to be locked and there won't be interruption from one print and the next one. Okay, so if we run, we see this mixing of the threads. And now, what would be the solution of Python to avoid something like this? So to use the global interpreter lock. So we are going to simulate here. So we have a lock that the threading module gives. And these are the same functions, but now before the printing loop, we're wrapping it by loop lock acquire and lock release. Okay, and here the same. So this means that when these threads start, it will acquire the lock. So it's going to block the thread where the other function is running. It will do the whole thing, the whole printing, and at the end it's going to release the lock. So the other function can run, or itself can run again, depending who gets the lock the next time. So if we do like this, now when we run, we see the two independent executions. Okay, so this is how Python is written. Everything in Python will look will do something like this in this way to avoid this. And you can imagine the reason why this is happening. And it is related to the reference counting and garbage collection. So if two threads of Python are running at the same time, and one thread, it can happen that one thread creates something and the other one deletes something, and they can at the same time write on the reference, which is a variable itself, and can corrupt this value of reference. And to avoid this happening, because this can create problems like if something that is not supposed to be marked as a reference 0 is marked as a reference 0, then the garbage collector will mark it as free. And then when you try to access this memory, Python will tell you this memory doesn't exist anymore. And or the opposite, something that is supposed to be deleted is not deleted, and it can create with time memory leak, and your memory can explode. And so this is the solution of Python, to write the Python code itself in this way using locks. Okay. So I'm going to check the chat if there are questions. No. That's it. So in Python, I said that everything is written like that, but there are two ways, in fact, that the lock is implemented. One is called CPU bound, which is for everything that uses a lot of CPU and needs CPU operations, like doing operations on lists, or most of the things in practice. So they are written like this: acquire lock, do something, functionality, and release the lock. Okay. And there is another type that is called IO bound, that is waiting for OS calls. That can be writing a file to disk, or can be the sleep function that sometimes we use to test stuff, that is time.sleep. And this one is also IO bound. And these ones are implemented the opposite. They release the lock before starting and then acquire it afterwards. So which means that something like a sleep, if you put it in a multi-thread environment, they will run at the same time. It will, if you have two functions that do sleep, and you're running a multi-thread environment, they will run in parallel. Okay, these ones they won't. This one will be locked like the example with the single colors. Okay, and in Python, in NumPy, the thing is different. So NumPy is written for numerical calculations, and these numerical calculations, in general, they benefit to have multiple threads because you can unroll loops and do many things in parallel. And what NumPy does when it has to do things that that are in Python itself, you can see things like this. This one can be, for instance, a C macro that it says NumPy loop begin thread and some functionality, and NumPy loop end threads. And these are calls that the NumPy is doing to release, to force release the Python, the GIL, so the log of Python, so it can do multi-threaded things. Okay. Also, in NumPy, if something is pure C code, then C itself doesn't know about the GIL, so it can create new threads without having to do anything. And yeah, I think for this part that's it. If you have questions, you can put it on the chat, or later. Doesn't have to be now. We can discuss about it, and we can. Let me say time 9:50. We can continue to the next part of the talk. Let me just check quickly something. 9:45. It's 9:50. Okay, we are pretty much on time. And so the next part of this morning, we are going to yeah, as I said before, it's going to be a refresher on NumPy, and later we are going to see some basic profiling of Python code, and all this part will be in the afternoon and on Thursday, but it's the same slide for everything. So NumPy, for sure, most of you know well NumPy, or at least have been in contact with it. But anyway, let's go and refresh it a bit. NumPy is a Python library that brings the support for multidimensional arrays and matrices to NumPy, and it is a collection of functions to operate on these arrays, and it's in general is the building block of numerical Python, and also the first place where we stop, where we go to learn, when we learn something that is numerical, or we always go through NumPy and learn it, and maybe from there we go to another library that builds on it. So NumPy, the center of NumPy is the NumPy ND array. So the NumPy ND array is a powerful multidimensional array object, and with it you can apply many functions of NumPy that are very sophisticated and often written in C. Among these functions, there is many functionalities like linear algebra, Fourier transform, and many random number capabilities. Besides that, NumPy brings something that is called F2Py, which is a code, is another it's a binary that is a program that helps you to create bindings for Fortran code. So with this one, you can easily write a Fortran program and call it from Fortran, so routing or something, and call it from NumPy, and we're going to see it in the afternoon. So NumPy is compatible with C, and something that is very important now is that many libraries implement the NumPy API, such as Dask and CuPy, that you will see tomorrow on Thursday. And this is very convenient because well, the API is the same. You learn one API, and also parts of the API you can reuse. You can combine them. So to Dask you can pass a NumPy array, and it will know what to do with it, for instance. And this is very convenient because we learn one thing and we can do a lot with it. So we can scale to multiple nodes, and we can use GPUs basically by knowing the NumPy API. Okay, so I put here, this is a link to an app. This is an extension proposal for NumPy that you can have a look afterwards if you're interested in how these things are intended to be implemented. Okay, together with NumPy, we always put together another package that is called SciPy. And SciPy is, you can see it as an extension of NumPy, and it brings many more functionalities to operate on the NumPy array, like numerical integration, there is interpolation, optimization, more linear algebra, and statistics. And yeah. Okay, so NumPy array. So before doing some demos and things, let's talk a bit about the internals of the array, what the array is, and how it works in the background. So in the terminal, when we have a Python shell, we know this is something like this, looks like this, the NumPy array. For instance, in this case, we are saying x is an array with this shape and type int 8, and this one is we can see it in NumPy as a matrix, a 3x3 matrix from values from 0 to 8. But in the backend, in the internally, the array is one part of the array is a block of memory that has these numbers. It's something that looks like this. It's not really I put it rectangular for visualization, but it's a continuous block. So this one continues on this, and here there are all the numbers in binary. And so if we for visualization we mark if the numbers here, we see the 0, the 1, the 2 until the 8. Okay, so this there is this part of the array. So this is where the data is stored. But this block of memory doesn't have any information on what is the organization of this on the array and what is the shape of the array. So together with this, the NumPy array has something else that is a metadata. Metadata part that it gives the interpretation, the NumPy interpretation to this memory. There is the shape, there is strides that we will see what is it. It's related to the order of the numbers inside of the array. There is the type, and yeah, many things, dimension, and yeah, many things for NumPy understand what to do with this block of memory. And so this one here, we call it data buffer. It's called data buffer. And this one, metadata, as I said. So this data buffer is stored in the same way that a C code, a C array will be stored, which is row major. That this means that as we go here in this direction, it will go through the row. For instance, this will be the 0, the 1, and the 2 that were in the first row, and there will be the 3, the 4, and so on. And something very important in NumPy is that the NumPy array can have only one data type. Okay, so this block of memory in the metadata will have the type, and that's it. This will be that type. And let's see an example how quickly how it works. So this is another data buffer, the same thing that we had before, but now with decimal numbers instead of binary for us to understand better. So and in NumPy is we have this metadata, and this is the interpretation of this memory. Okay, and we have the type. So each of this one is going to be a byte, so 8 bits. So this is 1 byte, 1 byte, 1 byte, and we have the shape. So it's 4 by 4. And finally, these strides. The strides will set this number. This order that is here. So if we have 4 1, the order is this one, and if we have 1 4, we have 1 4. The order is going to be the transpose. Here I messed up this number. I realized earlier today. So this one should be 11, 12, 13. Okay, and but yeah. So with the stride, by changing the stride, this number, NumPy can do a transpose of the matrix without having to change memory, which is expensive. So and how this works? So the stride, the first number of the stride, it will tell NumPy how to look up here from one row to the next. So for instance, from this 0, from this row to the next in the same column, NumPy knows that it has to move 1 byte. So in this case, from here to here, to look up in this memory block, NumPy moves 1 byte. And the second number, it means for that from one row, column to the next, NumPy has to look up in the memory, in the data buffer. It has to jump 4 bytes. Okay. Now, when the transpose is done, that is only to change here 1 to 4 to 4 to 1. Now, so the 0 is the same in the transpose, but NumPy to look up the next row, it has to jump 4 bytes. So now there is a 4 here in contrast with before that there was a 1. And to move in a column, it has to jump 1 byte. And there is an expression for the lookup of the NumPy array. So if you give 2 indexes like 1, 2, which is 6, NumPy will look up here in the data buffer using this one: strides, the first strides times the first index plus the second stride plus times the second index. And this is how NumPy works in the NumPy array. Sorry, works in the background. And this can be important to understand it, because yeah, we can understand things like doing this operation of transposing. Now we can know that this operation is not creating new memory. And we will see later another kind of operations that we can know by knowing this that doesn't change memory. And the opposite, sometimes we know when the operation will need to require new memory. Okay. So this is all about the internals of the NumPy arrays that we want to show you. And we created a homework for you that is the notebook in the folder NumPy01. And this one, you can play with these things with the arrays, just to, sorry, with the internals of the array, to try to understand better how it works. And there are 2 things. There are some examples where there are different shapes of NumPy arrays, and you have to guess and then check what is a stride. And afterwards, there are some simple operations that you have to say if they can be done only with metadata modification, or they need to change to create a new data buffer, to create a new data. And again, this is for homework. So we can continue with NumPy. Okay, so now more in practice. This part is mostly to show you how to approach writing NumPy code. Okay, and the most important thing in NumPy when you write NumPy code is vectorization, and this means that you have to write your code in such a way that operations are done over the whole array, instead of looping over the values of the array. Okay, so if we come from C, for instance, we may be used to, if we have arrays, to loop over them to do operations. So if you want to do a scalar product or something, we would loop over the 2 arrays and do a scalar product. Or if we want to sum 2 arrays like this one, we may want to loop over these arrays. But in NumPy, operations needs to be done like this. In this case, we have these 2 arrays, and we want the sum of the arrays, and we simply do in one line set equal x plus y, and this will sum all the arrays of all the elements of the array. Okay, so this is very important in NumPy. So another important thing is to use universal functions, which universal functions are functions that it's a concept in NumPy. It's functions that get an array as input, and they give you an array of the same size, and they operate over the whole array. So in this case, if we want to get the exponential of all the elements of the array, we would do something like this: y equals np dot x of x, and in one line we will do the operation for all the elements. And besides universal functions, the abbreviation is ufuncs. We should use all the NumPy functions. So because NumPy functions, as mentioned before, they are very sophisticated and they are written in C very well, and they are fast. For instance, this one here, if we want to do the matrix multiplications, we have two matrices here. We can use this operation, x at y, which is equivalent to do np matmul x comma y. And this one will give us the matrix multiplication of x and y, if x and y have to be matrices. And yeah, this one is a really fast function, and even is multi-threaded. Later we are going to see in a demo that we're going to look to the top command while running this one. I will see that we'll use all the CPUs on the PCDA nodes. And finally, also important is to adapt your solutions to use these 2 points, in particular the first one. And sometimes the problem that we are working in is not really obviously vectorizable. But so if you want to do it with NumPy, if you do loops, you're going to make it, yeah, like plainly wrong. But also you won't use all the features that NumPy gives you. So it always pays off to think a bit more and try to vectorize. This is something that we're going to focus now in the morning in an example to see a case that is not easily vectorizable, but with the trick we can do it. Okay, so now we're going to make a quick stop in broadcasting, and we're going to explain what it is, because it's a very important operation that is done very often in NumPy. And broadcasting is called in NumPy everything that has to do with operations with arrays of different shape. For instance, in this case, we are summing a column array with a row array. And in NumPy, this is defined like this. So we create an n by n matrix. So we have n1 and 1n, and this one will create an n by n matrix. And it's going to be like this. You can see it as this element here, which is a scalar, is going to be in the first row of the matrix, summed by each of the elements of the matrix, and then the second one, and so on. Okay. So this is broadcasting, and we have prepared a notebook for you to play a bit with it and understand broadcasting in different ways, because yeah, part is very important in NumPy, and second, we're going to be using it afterwards for a demo. Okay, so let's go now to NumPy 002 broadcasting. Oops. All right, and I will introduce you a bit to the notebook, and then I will give you some time to play with it, and afterwards we will discuss it. So before anything, let me just give you a 5-minute tour here on Jupyter. So in Jupyter, when you arrive, I think you should have done this thing already. So if you have the Jupyter notebook already running, you can go to a terminal if you didn't do it. I already had one. And go to the general channel that this same information is written there. just scroll to the top. And so this is what I explained in the morning. If you didn't do it, we can do it now. So we get this this thing in the setup point. So we copy this one and we run it. So just like this, enter. And this one will create a Jupyter kernel. A Jupyter kernel, you can see that's an environment or an executable with an environment for our course. Okay, so you run it and this is not going to do anything. It's just like this. And so now, if you're doing it now, just refresh the tab where the browser tab. So I cannot show it here, but just refresh the tab. And when the Jupyter comes back, okay, not here. So if you go to a terminal, to a notebook, you will see here kernel. If you go to change kernel, there will be HPC Python 2022. Or if you are in an empty Jupyter, you will see something like this with less stuff. But you will see something called HPC Python 2022. Okay, and yeah. Besides creating this kernel, this script that you just run is going to create a link to Scratch in Pysdint, because Scratch doesn't it's not accessible from here directly. So now you will have a link. The thing is just called Scratch, and you can browse here and find it, and then you will be in your Scratch, and this is where you will have your clone the repository. If you didn't clone it, you can just come here as we did before, go to Scratch and copy the line to, well, I don't have it here, but from the general channel, cd scratch git, and this one will clone the repository. And if you are in Scratch, you can navigate to the repository. It will appear here after a couple of seconds if you're already in Scratch. And yeah, so wait, sorry, I don't have mine in Scratch. Git Python HPC. Okay, and then we go to NumPy, and let's open the second 02 broadcast. I think I can zoom a bit. Theo, could you check if the size of the letters and everything, the numbers are fine in the notebook, or should I zoom more? Okay, thanks. So let me go to the chat. Okay, no questions. Okay, then I think you should have it. So I will give you a quick introduction to the notebook and maybe to Jupyter. So again, here you should see the kernel. So here goes it will be written the name of the kernel. If you have something else like Python 3 or something like that, just click on it and open, and then you will see a list of kernels. It's not as big as mine, but you select HPC Python 2022, and that's it. This is the kernel we're going to use. And if you haven't used Jupyter or Jupyter Lab, yeah, it's just like it's a fancy shell, and you have these cells here, and you can run them, and the code stays there, and you can go back, and so everything stays in memory. It's a single script, and that's it. And then with Jupyter Lab, you can do things like this one, for instance, and you can put your top command. You have it. Okay, the top command, and you can see the CPU, and yeah, this one can be useful if you want. And yeah, the rest is like normal Python, and there shouldn't be any problem. I'm seeing some questions. Let me just go there. So there is someone got a strange error. I don't know, maybe if that's the case, just check that the kernel is the right kernel and just restart the kernel. So you can restart the kernel. So this kernel is running, it has many things in memory, everything you're running here, and then you can come to kernel and do restart. And yeah, now if you run again, so you see that this is 34, it will start as 1. It will be the beginning of the notebook again. So anytime if you mess up something or you want to try something different, you can just come here and restart kernel, restart kernel. Okay. Okay, just please let me know in the chat if the error disappears with that. Okay, so now it's 10:15. I think yeah, we have seen some yeah, some material, and maybe it's a good moment to stop before going to this notebook. And so let's make a break of 15 minutes and come back at 10:15. Sorry, at 10:30, and yeah, we're going to continue with the notebooks. Okay. Okay, we are back. So we were about to start this notebook. I hope that all of you managed to have the kernel. And yeah, so this notebook starts in the same thing we were before in the slides. So it's called Basic of Broadcasting, and the idea is that you play a bit with broadcasting and try to understand how it works and the kind of things that you can do with it. For instance, yeah, no, sorry. Yeah, so the starting point, I think, to understand where the broadcasting is to see it in its basics, in the more basic case, which is something like this one here, which is an array that is going to be summed to a scalar. So this one is going to be going to give you A plus the scalar, B plus the scalar, C plus the scalar, and so on. And this is very similar to what we saw before in the 2x2, that but instead of a scalar, there were many. So there was a column of elements. So we got a different rows in a matrix. Okay. So this is the basics. So now here you can check it. And NP range will give you 0, 1, 2, 3, 4, and then by adding 1 to the array will sum 1 to the whole thing. Okay, so this is very simple. And now a very important part in broadcasting that it comes very often is adding new array dimensions. So you have an array like this one, for instance, that we just saw, NP arrange 5 is 0, 1, 2, 3, 4, and the shape is 5. We can convert it. This is an array that it behaves like a row array, but we can give it a more explicit notion of row array or a matrix of one row, or a column array, so a matrix of one column and multiple rows. Okay, and for that we can use this NumPy functionality that is called NP new axis. So our array here has only one so it's one line, the 5 elements. If we do x, it looks like this. And if we do, this is just notation. If you do like this, it means like here, all the values of the array. Okay. And so we have, you see, we have one bracket is 5. If we do add here NP new axis, so it's together everything that it has plus a new axis. Now it will look like this. So, and this one, now you can see it as a matrix where each row is one element, so which is a column vector. Okay, so you have here a column, and those are the rows of one element. And now if you check the shape, this one to compare to this one, this is going to be 5, 1, and 5. So it's the same content, same data, but it's organized in a different way. And yeah, you can do the same thing. You can add also more new axes. You can do like this, and whatever you need. Okay, so this is 5, 1, and we can put it first before, and we can do each new axis and then all the content, and this is going to be a 1, 5, and it looks like this. So now if you compare this one, it has one bracket, and this one has 2 brackets, and this is a matrix with only one row and multiple columns. So they will be the transpose of this one. No? So if you do transpose to this one, you will see this one here. All right. And here I put a couple of questions. What is the difference? The difference is what we saw here. And what do you think? This will allocate new memory. It will need to allocate new memory, or with the simple metadata, something like changing the strides or changing the shape. Is it possible to describe the new shape? No. So this one we discuss it when after I give you some time. And this part is things that you can do with this information that I just gave you, with creating new dimensions and broadcasting. And things that you can do is something like this. So let's say that you have this array 0 to 4 of shape 5, and you want to get to all the combinations of sums of all of these elements. Something that you can do, so something like this, is just to add new dimensions, make one a row, so a row and one a column, and that's it, and you get a 5 by 5. If you print here, you see all the combinations, okay, the sums of the combinations. And this is something that it comes very, very often when doing NumPy. And so that's it. And this one can get more complicated. So the next step of complication is that each of these are vectors. So it will be this case. So imagine that it's exactly the same thing, but now A has a 0, 1, and 2. And if you look like this, imagine that they are in a dimension inside of the screen. So you have the vector A, and in the screen a 1 and 2. So it's like a matrix horizontal. So that one is going to be very similar to this one. So it's going to be the same way of the combinations are done. No? All of this by each of the elements on the column vector, but and the last dimension, they say this 3-dimension vector, they are going to be identical. So they are going to be 1 by 1. So this one is easy to understand. And here, if we look at the shapes, even better. And we have 1, 5, 3, which is this one, which means 1 in this direction, 5 columns, and 3 in the direction of the screen, with a 5, 1, 3. So if you see, compare this one to this one, you have the beginning is the same, so it's 1, 5, 5, 1, 1, 5, 5, 1, but they have a 3 and 3 in the last dimension. So this last dimension, they have to be the same. And if you sum it, you get a 5, 5, 3. Okay. And yeah, so here I give an exercise, which is to so you have a list of vectors. So they give you a list of vectors. Forget about NumPy at this point. And one vector is x1, which has x1, x1, x11, x12, x13, and another vector is x2, x21, x22, x23. and you want all the combinations of subtractions between all the vectors. So you want x1 and minus x2, and you want x1 minus x1, x1 minus x2, x2 minus x2, x2 minus xn. So you want all the combinations of subtractions. And yeah, and the exercise is based on these things, which is pretty much the same. How can you do that? Just to explain here what we are doing at the beginning. We are generating random numbers, and this is a new way that is advised to use now random number generators in NumPy. So NP random still works, but this is what they suggest to use now. So you create first a random number generator object, and with this random number generator object, you can generate different distributions. So for instance, this if I run it here, RNG, there is binomial, there is chi-square, they have put many things there. It's a more organized way to do it, apparently. And we are using random numbers. So we generate some data and then we do it. And so this is to solve this problem, and it solves. So the thing is, I will give you now 10 minutes to go over the notebook. It's 40, so at 10:50 I come back and we discuss quickly the notebook, and just play a bit with it and try to understand how broadcasting works. So always try to put it so to understand this one, try to put it in the example of this one, and to understand this one, try to put it in function of this one, and so on. Okay, see you in 10 minutes. If you have questions, please in the chat. Okay, we're back. So let's have a quick look to the final exercise. And if there are questions. So here we generate this data. And it's a 10.3. So we put this data that the exercise is talking about as an array where these are going to be the vectors. No, these vectors are going to be like this, and these are each of the vectors. So in the rows, every row is a one vector, and the columns we have the components of a vector. We organize it like that, and this is 10.3. And so to get all the combinations, we cannot get it like this, in this shape, because if we sum, we were going to get one by one, so column by column, so row by row and column by column. Yeah, no, just row by row, and column by column, sorry. So we create a new axis to make it look like this. So now this one, you can see it like this, like we're going, so let's say that we have it visually like this, and we're going to put it one like this, and the other one we're going to put it like this, and the components are going to be one-to-one, so we can sum them. So we apply this NP new axis in the first one and in the second component, so they look exactly like this. Now we have 1, 5, 3, in this case 1, 10, 3, and 10, 1, 3. And we will get our 10 by 10 by 3 matrix. So we get this one and this one, 1, 10, 10, 1. So all this, we get all the combinations, and the threes, the component of the vector, we don't want to mix them. And that's it. We do like this, and we get our 10 by 10 by 3 matrix with all the combinations. Okay. There is a question here. No, something that I missed. Okay. No, sorry, it's not that. Okay, we can continue with the presentations. So now we know, understand a bit of refreshed broadcasting. And at this point, I want to show you a problem. So we can apply these 3 points that we saw before of NumPy on about vectorization and about rethinking your problem in a vectorized way and using Python, NumPy functions. Okay. So the problem that we gave to you, we brought to you is determining the Euclidean distance matrix of two lists of vectors, or one list of vectors. So we have these two lists of vectors. So it's the same thing that we saw before. Each of these are a vector, and yeah, we can put it in an array the same way we did before. And this one is the same. And we want all the combinations. We want all the combinations of the Euclidean distance of each vector. So before in the exercise, we saw the combination of the subtractions. So now we want the combination of the Euclidean distance. So we want these two will give us this Euclidean distance, and we want this combination of these two will give you this one, and so on. So I went explicitly and put all of them. And so this is the problem that we want to give it to you. So it's something that you may think about first about iterating and combining things. And now that we know broadcasting, we have an idea how we can start approaching it. And okay, so this Euclidean distance, so it's this geometrically looks like this in two dimensions. It's like the basic distance that we use normally in practice. And that's it. And we have a second problem, which is exactly the same, but instead of using the Euclidean distance, we are going to use the city block distance, or it's also called Manhattan distance. And here, instead of using the squares of the subtractions, the sum of the squares of the subtractions, we are going to use the sum of the absolute values of the subtractions. And this one geometrically looks like this. So it's the absolute value of one vector plus the absolute value, of the difference plus the absolute value of the difference in another component. And that's why it's called city block, because it's the distance in the blocks of buildings. So in a taxi, if you go from here to here, you would go through this city block distance. And this is an operation that can appear in some methods of machine learning. So you need to compute this city block distance matrix or the Euclidean distance matrix as intermediate part of some machine learning methods. Okay, so yeah, so we give you these two problems, and let's see the implementation that we can do with it to showcase the mindset and the way you should approach writing problems in Numpy. So this one, this is the most intuitive way of doing it. Moreover, if we come from C, that the idea would be to iterate over X and Y and get all the combinations and use this matrix product here to get the scalar product, which is the distance matrix. And this one is not good. So first, we are not doing operations over the whole array. We're iterating over the array. So this is wrong in NumPy. Plus the fact that doing Python loops is known to be very slow. So it's not efficient for a numerical solution of a problem. Okay. So we use some Python operation here, which I think now, thinking twice, I think this two needs to be matrices and not 5, like n vector. It has to be like n1 and 1n. So, but we use some Python function, but this loops makes it so wrong that it's so slow that this is doesn't make a difference. And we were lazy, and we didn't think any vectorized solution, how to adapt our problem to a vectorized solution. Okay, so this one is something that you should avoid always in NumPy. Okay, so let's consider now a better implementation. So now that we know broadcasting, we can do something like this. So we can get the same operation that we did before. So we have this list of vectors, and we combine all the subtractions. So at this point, we have all the subtractions, and we have n by n by 3, let's say, matrix. And the only thing that we need now is that this 3 dimension, the last dimension, we need to apply the the Euclidean distance. We already have all the differences, so we can square the difference. So this time this. So now we get the squares of the difference, and we sum them, and we write here axis equal to, which means that we are summing only the last axis, this dimension 3. So this one will give us the Euclidean distance matrix, the n by n matrix, with all the things summed. So this is one implementation. Okay, so don't worry now, you will have time to play with it in 5 minutes. And we have a second implementation. And the second implementation, we think a bit more, and we can find, if we think a bit more, we can find maybe some trick or something that allows us to write to find another solution and compare the two implementations that we did and see which one is faster. Okay, and this is a known trick for this. And the thing is that the Euclidean distance matrix of you can rewrite it like this as a scalar product of the differences, and the scalar product in turn you can write it like this. So notice here that here we have II, so same index, so it's column to column, sorry, row to row multiplication. And here we have YY, it's exactly the same thing, so column to column. And this one we have IY, so we have all the combinations of the rows and columns. So this one here is a matrix multiplication. So for this one we can use matrix multiplication. And for this two, we can use another trick. But the point that why we did this is going to show now is because Numpy has very fast solution for all of these operations. So this one, the one we know, this is a matrix multiplication. If we put the whole, the whole list of vectors, not every vector, but the whole list of vectors, this is a matrix multiplication. So we can use this x at yt. So this is I showed it before, but this is again the a syntax for matrix multiplication. It's equivalent to do mat mul of x and xt. So it's a matrix product. So this one we have it very simple, and these two we can use. There are many solutions, but the fastest that we have seen is this operation that is called NP einsum. It means Einstein summation. It looks a bit ugly, but it's just a summation, and you set the indices where the summation is going to happen. So this thing means this operation here means you have xx, so x yj xyj by summing by j. So it's x squared ij summing by j. So this one will give you a vector with this operation for every I. Okay, it looks ugly, but you will have time now to play with it again. And the same thing for y, because it's jj, the same index. So we have now all these things that we can do in NumPy very fast, and now we just have to sum them. But to sum them, notice that this one is ij, this one is jj, and this one is ii. So this part here, we will need to do a broadcast operation to get all the combinations I and y. Okay, so we do this, and now we sum the whole thing, and we can put it together in a function that we did before with the broadcasting. So we get the two einsums, the x2, y2, and xy. We apply the matrix multiplication, and notice here that we use transpose here because remember matrix multiplication has to be mn and m. Okay, and finally we sum all the components. So x squared, y squared minus 2 xy, and this thing numerically when x is equal y, it can give values very close to 0, but like 10 to the minus 11 or something like that. But sometimes it can give negative values because the numerical error at the end for the very small for the last values after the comma. So we put an abs here to have always positive, to have always 0. Okay, it's just about convention. In practice, right now we don't need it because we don't do anything with this one, but in practice you may have to do this. Okay, So we have these two implementations. And now we have a notebook, so you can go over it. So the notebook is, oh, I don't know if the number, so the name is not right, I think, but so the notebook, I'm sorry, it's the next one inside Numpy. This is 3 Euclidean distance matrix, Numpy. Okay, so I can start closing things that agenda, maybe not. Broadcasting, yeah, should be fine. Okay, so we have this one, 3 Euclidean NumPy. Just check that the HPC Python 2022 kernel is there. And so it's 10. Okay, yeah, we have enough time to play with it and try to understand. And so this notebook is we give the two implementations. So we have this one using broadcasting. We call it Euclidean broadcast. We have this one Euclidean trick, which is the second implementation. And we want to see which one is faster. But also there is some section here for you to, if you want to understand in detail how this functions, you can read it and go through it. There is an explanation here how it works. And we also check different solutions, why we make some decisions, like why we went here for INSUM and not something different. And that one we check. Yeah, we check it here. We have two solutions for the same thing. Instead of INSUM, we could have done x times x and then sum over the vector dimension, so the x-axis one. But yeah, it turns out that one is faster than the other one, so we went for this one. But yeah, you have time to play with it. And then we check the times of both solutions, and we check that they both give the same value. And this is two ways to check the results. So here we just compute and get the absolute value because of the we get the absolute value of the difference, and we get the maximum, and we check the maximum is lower than the tolerance. Or you can use NP is close. So NP is close is going to get the difference between two things that you give. And in this case, this is those are arrays. It will give an array of booleans with true or false. And if there is a component, an element of this difference that is larger than a tolerance that you can specify like this tolerance. Actually, one nice thing of the notebook, if you are not used to it, is you can do NP is close. Sorry. For Numpy. NP is close, and it will show you the things. So you can specify a tolerance and use it like that. And then here we check that there is no false inside of any of this of this array of booleans, which means that none of the difference between these elements is going to be large than a tolerance. Okay, so yeah. Here I will give you now time. Just please, again, about this part, if you want to understand how the whole thing works technically in Numpy, I think you already know what is happening in the notebook. But you just go over it, and here I put you some tests so you can test some things. But don't get too obsessed with it. Just the main idea of this notebook is to show like the two implementations and how we can find different solutions in Numpy to speed up our code, and just the general idea how to work in Numpy. But we don't want you to get now to I don't know to spend time in a particular function or something like that of Numpy. So it's 11:07. I think yeah, we can come back at yeah, I can leave you until 11:20. So and maybe a bit more if you need more time. And yeah, go through the notebook, and you have questions. Yeah, let's discuss about it. So here for this notebook, I can give another 5 minutes. We have more time. We have plenty of time now in the afternoon. We have just a little bit to finish only. So let's come back at 25. Okay, let's discuss the notebook. Yeah. Sorry. So we come here. So here at the beginning, we have a question about this. That is, if you see something bad about it, and if you thought about it, we will discuss it now in the profiling part. But from the implementation, maybe you can catch some problem that this implementation might have. Okay. So just quickly over the implementation. So this one, XY is the matrix product. I think this one is pretty easy to understand. We do the matrix product with all the data at once, which is exactly what we want, and with all the X, with all the list of vectors and all the Y's and all the Y's, and that one will give us all the combinations of the scalar products. Okay, so this one is more clear because we are used to matrix products. So now InSum is going to be a sum over the J in this expression here. So the meaning of this one, so InSum stands for Einstein summation. This is a common thing if you have worked with tensor algebra. But this is just a way of expressing the operations, and it means when you have an operation like this, a notation like this, xik, ykj, in Einstein summation notation, it means that there is a sum symbol over the repeated index. So in this case, k is repeated. Then this means that the summation is there is a summation over k. So these two things are equivalent, and this is what InSum has in this part. InSum has an extra, it's an addition to the notation, which is this arrow here, that it means okay, sum by the repeated index, which for us would be both of those, because here in principle there should be a sum over I and a sum over j, but with the arrow it says don't do the summation over I, keep it as a vector. So it knows that every element of the vector then have to be I. Okay, so if you put b something or k some here, then you will get something completely different. But in our case, what we want is that we have the data, so rows of data, and we want to multiply each of them, column, so row by row, like this, xy, or yj, no, sorry, xi, or yj. So one by one, and then we want to sum over the short dimension, so the dimension of the vector, not of the list of vector. Okay, and this is actually what is happening here. And this function, it requires a bit of practice if you want to use it, and I don't know if it comes too much in Python code in general. If you go around to different Python, NumPy implementations, but it's a very convenient function. And if you have, I don't know, you want to do an operation of summing in an array of 3 dimensions, maybe it doesn't make sense to use it, because if you share the code with someone, or even for you later, after a year or two, maybe it will take you time to understand what you're doing there. But it's better to use .sum, and that is more clear. But for something that maybe is a very long array, or you have some complicated summing, this INSUM is very efficient. The only thing that is not multi-threaded, everything is in a single thread. But besides that, it's very well implemented, and it's extremely fast. Okay, and okay, so let's try it here. So here the data looks like this, same that we have had in the. Actually, this is 4. Okay, you can come here. It would be the same of these ones, no? And each of these are the vectors. And so as an example, if we do this INSUM operation, so here you can write other things, but if we do this INSUM operation with XX, it will give us a matrix of 10. So 10 is this dimension here. So this means that this one, it will multiply this one by row. So this one, this row by this row, this row by this row, and it will sum over this dimension, okay? Keeping these ones apart, not sum. Okay, so this one will give us this. Now, for instance, if we do like this, it will give us a scalar, because now there are double summation for I and for j. So here we have I, right? Okay. If we have j, you should expect that the shape is going to be 3, right? It means because we are summing now in this direction. Okay. And okay, so with the new axis, I think you understood better from the previous notebook. And this is what we are doing. This is what we are doing with these two terms. Okay, so we apply the broadcasting. In this case, we don't do apply broadcasting twice, but we do a transpose. That would be equivalent in this case. Now. The other one is matrix multiplications. So we have a 10 1, and we multiply it by a 10 3, and we multiply it by a 3 10, and that will give us all the combinations of these elements here. So this one, if you don't get it very well, maybe you can write by writing the definition of the matrix multiplication later in a piece of paper. You will see. But technically, NumPy wise, it's easy to understand what is happening. Okay. So this one, what I was commenting before, why we use this NP INSUM, that is a bit hard to understand, instead of this. So this one is more obvious what it means. It's more transparent. So it's x times x. So you're going to multiply all this. So you're going to get the squares of all these values, and you're going to sum in the short in this direction. But we measure here the time, and we see that well, it takes some time, that the INSUM is going to be faster. So here we have 1.131 microseconds for INSUM, and sum is more than double. And for bigger data, this difference maybe it can be even bigger. So that's why we went for INSUM. And this one shows again that it's very important to try different solutions. If you have something that is delicate, that it can be time consuming, just try to, if you have time, employ some time on finding different solutions within everything that NumPy gives you, and compare them. And here we're going to talk about this later, but time it is it's not a Python thing. It's well, it's a Python thing, but this command itself is something called magic commands of Jupyter that start with the percent. And this one, so you see, give you 131 microseconds plus some variance per loop. So this one, you run this one, it will run whatever you passed many times, and it will get some statistic. It will give you the mean value and some variance. And yeah, that means that it run it. It ran. This means that it run it 10,000 times, 7 times. So he did a loop, it runs 10,000 times, got some statistics, did it again, and 7 times, and from that he got this final value. So that's why it takes these microseconds, but it takes like 2 or 3 seconds. Here it says 1,000 instead of 10,000, because depending how much it takes and how dispersed the values are, it will stop. It will say, okay, with 1,000 is fine. All right, and this one I just put it there for just for you to have another way of doing it, since we are talking of different implementations. But this thing, I think in practice, it will be equivalent to this one. And what it means is that using the addition operation, apply it to the direction 1 of the array. So in reduction means that if you have one array, a reduction operation is to get a smaller array or a scalar out of it. And this one means reduce, so make it smaller by adding all the elements in this direction. That's what it means. But in practice, I think it's the same of this one. You see here, the time is the same. And here we get to the comparison. And I want to show you here, if we put the terminal here and we do top. So we can look here at the CPU, and we can see how many CPUs is using. So if we do like this, let's run first. No, this thing won't move. So let's run first broadcast. So here we look, and we have a 98, maybe around 100% of CPU. This means that one CPU is being used. Okay. So it takes 1.76 seconds. And again, this operation is vectorized, the broadcasting, because we want one line of code. This line of code here, we do operations over many elements at the same time. So, but it's not, doesn't happen in parallel. Okay. And now let's try the other one. So Euclidean trick. So this is 1.7, almost 2 seconds. And Euclidean trick, let's go to look at the CPU. And now we see 1100. And that's it. Yeah, it finished. So this one is multi-threaded. And it's not, this multi-threaded part is not in sum, it's the matrix multiplication, the add part. Okay. So let's run both of them. And to see the comparison, to have the comparison 1-to-1. So again, this is now broadcast, Euclidean broadcast is running. And when it returns, we will see that, yeah, now we'll see that it will, yeah, there are many threads running. And that's it. And here, these functions can be multi-threaded in parallel. Thanks that Numpy, as we talked in the beginning, releases the GIL before doing the operation. Okay, and that's it. Here we can check that they give the same value. So 10 to the minus 12. This is perfect. And here there is no false inside of this. So if you remove this part, maybe I close this. You will see that it gives a true for every difference, and we check that that there is no false in this because we're going to see all of them. and you see it's false. There is none of them that gives you a lower number than the tolerance. And you can select the tolerance you want. And here I put a homework that we're not going to discuss, but you can do a solution by doing like this. Try to, just for fun, it's not really anything extra you will get, but try to use the final summing of the last element and the squaring with and sum in this implementation and see what happened. And then you can check this one afterwards. Right now, I want to show you, we continue with this idea, and I want to show you the profiling options that we have here in the notebook. And I mean, there are more sophisticated things, but this is like the minimum, very easy that you can do to check your code. So here we have, let's go to the profiling notebook. In profiling, sorry, let me just show again. So now we are here in HPC profiling, and then go to the first one. So we have the two implementations. We generate some random numbers. So the first things that you can do to profile is time it. Time it, we already saw it. There is some statistic. And I think, so you can do like this. Control C. Let's wait a bit. Okay, so we know only by timing it, we see that one is faster than the other one. Actually, way faster than the other one. And if you do like this, you can see that time it, these magic commands, they have a help. You can set you can play a bit with the statistic by using, putting the time, how you're going to measure it, or how many loops you want to do if you don't want to wait that much, or if you think that you need to wait more, that automatic is not good enough. So there is some options you can play with it, but in general, most of the time it's used like this. Okay, so this time it is a very simple way of knowing about your code. The other thing is line profiler. It's a Python package that has an extension for Python. You can use it also in the terminal. And here, this one enables a magic command called lprun, it's line profiler run. And we do lprun minus f, a function, and then we put a piece of code that contains this function, and then it will give us this. So this is what is going to run, and it will be looking at Euclidean broadcast, which is the whole thing that we're running. Anyway, so we'll give you a more detailed thing than time it. And here it goes by line, and it will measure the how much time, and they give you the percentage of time of every line in your code. Okay, and so this hits means how many times this line happens. In this case, 1. But if you have a for loop, it will tell you like 10 times or whatever times that your for loop has. And here is the time, a time per hit, for us the same because it was only 1, and the percentage. And it's a very nice thing that you can do. You can have a quick view of the profiling of the time per line without having to go line by line and generate data and check them. So it's a very quick way of checking. So there is no statistics here, so it runs once. And yeah. So this one is for Euclidean broadcast. For an Euclidean trick, we see here. So now we have the time. We see that the einsum parts, they are really, really fast. Which is understandable because einsum is a fast function, plus that we are doing one by one, so row by row operations. That is faster than doing a matrix multiplication that is a bit more complicated thing. And we see here that maybe not surprisingly that the longest, most complicated, most time consuming part of the function is the the ending where we sum all the elements. So maybe it can be worth to have a look if we can improve the way we sum these things, okay? Because we see that it's the slowest part. And another option that I want to show you is cProfile. And cProfile is something more detailed. So it will mention times too, but it will go through levels inside of your call. So here you see that it's calling reporting the primitive, everything, how much time they take, and some breakdown of time here. So maybe this one is more for developers, or if you are interested in the NumPy part. But it's another option that we want to show you because you may be interested. But these two, we totally recommend it. They are very quick way of analyzing your code. Okay, so this is line profiler. Line profiler is about time, but we also can profile the memory, and that one we do it with the notebook. Sorry, in the terminal, because it doesn't have a notebook extension. So we go here to, sorry, for you to scratch, me here, profiling, and yeah, let me just move some zoom window I have here. Yeah, so this one, to have the line profiler and to have the environment in the terminal. So if you do Python here, is the correct Python module of refrain of piecedint, and we need to activate the environment. So we can go to the general channel. That is the same thing that is written here, and the last in the block of information. Let's copy this one with a dot. Activate. Okay, and we put it here. And that's it. Now we have the profile, the environment activated here. So we are going to close here, and we're going to start with the main profiler. So main profiler, before seeing what is right, we can run it. Let's start with the 0 Python with the 02. And here we have something that looks similar to the line profiler, but now we are looking at memory. So here we have the function that we want to profile is our Euclidean trick, and it goes by line, and it shows you how much memory every line increases and the total cumulative memory. So so here we see that just starting the thing, the profiler and running the function uses 51 megabytes, and then we have this sum that use no memory almost. It's very small, so that doesn't add anything significant to the memory consumption of our function. And this one, the matrix multiplication at 30 megabytes, and the last one add another 30 megabytes, which is maybe to be expected because here this is yeah, here we have an n by n matrix, and this one also we end up with an n by n matrix. Okay, and yeah, we know that this one that we have here from the NumPy, that from the sum, that we did the new axis is on the create new memory. So this one, the memory, we should expect something similar to this one, or maybe something different because it's something intermediate memory, but we should expect something similar. Now, if we profile the broadcast, so here we went to 100 megabytes. Now the thing is different, and this is what was asked in the previous notebook. That if you could see something, some drawback in using this one, in this implementation. An advantage is obvious. We are using the vectorization, but one thing that is bad in this implementation, or at least not as advantageous with respect to Euclidean trick, is that this operation here will create an n by n by the dimension of the array by m. So n by n by m array. So we have now a cubic matrix, and here you see that this will consume 1.5 gigabytes. Okay, so this one increases a lot of memory, has a lot of memory, processes a lot of memory, but a lot compared to these 30 megabytes and 100 megabytes that we get in Euclidean trick. So that one can explain why this one is slower, and also because of the fact that it's not multi-threaded, but handling more data, it means yeah, it will take more time consuming. And here at the end, this one is a simple things, and it's 30 megabytes, pretty much the same than this one consumes, because this is the size of the array that we are getting, which is final n by n, because we got rid of this big array. Okay. And so the total memory here, it will be 1.6 gigabytes compared to this one, 100 megabytes. And this one is almost 2 seconds of execution for the size of the array that we put. And this one was in the order of milliseconds. It was like 6 times faster. Yeah, so I can quickly show you here. How this is done. So it's very simple. You load the mem profiler, and the mem profiler has a decorator. Whatever you want to profile, you decorate it with profile. And now you just run the function, and that's it. It's just to import something and add a decorator. And yeah, that's it. This is a very simple thing, and it can really help you out a lot with your implementation, and inspect very quickly the memory consumption of your code. Here, in addition, we give main profiler, line profiler, how to run it in a terminal. So there is no decorator. You can create a decorator yourself if you want, but so from line profiler you have to load this line profiler class here, and you create a line profiler object, and you similar to the decorator, you just run by hand here what you want to run, and you pass the arguments, and then it will run, and then you do LP print stats, and this will print it will be the same thing that we saw in the notebook. Okay, so we have here two very simple ways of checking the memory and the time consumption by lines of your code. And it's something that you can start with pip install. It doesn't require any setup or anything. And before finishing and going for lunch, so I want to come back here, and as a sort of summary. So we started. We saw a bit of the memory management of Python and the global interpreter lock, and then from there we went a bit about NumPy, and we learned a bit about the internals of the array. And I say a bit because it's really a very high overview of how things work. But we understand the basics of how the array works, and now we can decide, look at our code and decide for options and how we're going to do operations, and we can have an idea if something will use memory, will require new memory, or will reuse the same memory that already the array has, like the case of adding new accesses or doing a transpose. And this one can be very useful. And then we went over the vectorization in Numpy, and the main idea of today, I hope you got it, is that in Numpy the operations need to be vectorized. Is how Numpy is meant to be used, but in some cases vectorizing requires trying to rethink your problem in a way that is expressible, to express it in this way in operations through the whole arrays. And this is what we did today. And the last point is that it's always good to have different implementations, because sometimes it's not trivial to know what is more performant. And finally, using profilers. That is a very simple way of checking your code, that it can give you a lot of insight on what is happening. And that's it. So now, before just going to the afternoon, remember that besides the Euclidean distance matrix that we worked today, this morning, we also have the CT-block distance matrix. The CT-block distance matrix, you cannot apply the same trick that that we applied with the scalar product that we turn in different components, because the definition of the distance with the absolute value doesn't allow you to do that. So we have to do something else. And later today and on Thursday, and maybe tomorrow we will have a look, we will see that we have to go many times outside of Numpy to learn, to make fast our implementations. And this is what is going to happen for the rest of the course. If you have questions or anything, we're going to be in the chat. Otherwise, enjoy your lunch, and see you back here at 1 with Theo to learn about Cython. Okay, ciao. Thank you.
So we can slowly start. And good afternoon. My name is Theophilus Manitaras, and I'm a computational scientist at CSCS. So this afternoon we are going to see together how we can use Cython to more or less achieve close to bare metal speed on our machines using Python, but with some help from the syntax that Cython provides, so that we can speed up our code. And also, if we have time, we can see how we can wrap some existing C or C++ libraries and call them like we have written in Python, but taking into advantage the raw speed that Cython gives us. So just for your information, if you have any questions, please feel free to ask at the Q&A channel on Slack, and Raphael will answer, or I can stop and answer if it's something more general. So let me know if I go very quickly, or if something does not work for you. Let's begin. So we are going to open a new notebook based on the HPC Python 2022 kernel. And you see here that it opens the HPC Python 2022 kernel, but this will open a new notebook. what we want is go to Cython on the left side. This is where our notebooks are. In notebooks, and open the first one, Cython 1. Let me close the untitled one. So make sure that your kernel looks like that, which is the correct kernel that we have prepared for the course that offers you access to Cython. So HPC Python 2022. So let's start. Some initial stuff about Cython. Cython is more or less a superset of Python, which allows you to inject some specific information regarding types and other stuff to your code, which will, after injecting all this information, you can compile using Cython to C, the C programming language, and then this will be compiled to native code on the machine that you're running. So you can use Cython with all the Python that you have now, but in order to take advantage of the acceleration that you can get using the types that you inject from Cython, we are going to see together how you can do that and how you can take advantage of Numpy arrays, for example, for your numerical calculation. So, as I said before, every Python code, apart from some very special situation, is also valid Cython code. And I will make some import statements here. I will import Cython and matplotlib and NumPy and the math from the standard Python library and random. And then I use this magic, and this will allow us to use Cython from within this notebook, which in my opinion is much better for you in order to have an introduction to Cython. You can see what it's all about. So let's run this cell. So one application where we are going to compare how things look like with Python, and then we will progressively use more information to tell the Cython compiler how to compile into C code, is this Monte Carlo integration for calculating the value of pi. So more or less a way to calculate the value of pi is to have this square here, which is a 2x2 square. So its area is 4 units, and then start injecting random points inside this square and count the number of points that fall within the unit circle. So you see here, this is the unit circle, and the points, I hope you can see my pointer here, my mouse pointer. So the red points are here, the ones that fall inside the circle, and the blue ones are the ones that fall outside, but within the rectangle, of course. So we can more or less calculate pi by counting the number of points that fall within this unit circle. So with this simple relation here, with pi is close to 4, which is the area of the rectangle, and multiplied by the number of points that fall of the random points that fall within the unit circle, and the total number of points that we inject in this rectangle. So is recording enabled? Okay. So this is the pure Python implementation of this. I call it PyMC, Pi Monte Carlo. And this is a variable in circle, which is going to be used to count how many of these random points fall within the unit circle. So I loop over all these points. I create a random point with X and Y random coordinates, and then check whether this falls within the unit circle, within or on the unit circle. So then I can calculate pi. So I define this function and then I time it for 10 million points. So let's see how much time it takes. So it takes about 2.8 seconds to 75 seconds. And the approximation of pi is this 3.42. So it's quite close to the value that we are all familiar with. Now, let's progressively move to convert this code to Cython. So in the beginning of the presentation, I said that mostly all the Python code is also valid Cython code. So this is the Cython magic that we are going to use, which will go at the top of the cell and will tell the Jupyter notebook that we want to compile this cell using Cython. So here I just copy and paste the same code above. I just annotate it with the Cython magic. I compile it, and then let's time it. So just with using Cython instead of Python, we went from 2.75 seconds to 1.96. So of course, this is not how you would use Cython in your general calculation. You would not just compile your typical Python code with Cython. So this is not the speed up that you would be happy with Cython. So we are now moving progressively from Cython, from pure Python towards C. So with Cython, we can start injecting some more information for our code. And this information is going to be used by Cython when it produces the C code, then it's going to be compiled into the native binary, the native library that we are going to use through Python. So Cython has this keyword, the CDEF, where we use it to tell Cython that this is a static type declaration of a variable that we are going to use. And Cython knows, as far as it sees CDEF, that this is stepping out of the dynamic nature of Python, and it will produce efficient C code for this. So we know that our in-circle variable is more or less an integer, and our I, which is the index of the for loop, is an integer as well, and that the X and Y are double precision floating point values. So now I can specify CDEF for all of them, and again, I run this, and let's time now the code to see how good it is. So it is 459 microseconds, which more or less is 0.4 seconds. So we went from 2.75 seconds to 0.4. So you see that we got a very good speed up just by annotating these simple variables here. Also, as I said before, we will have this Cython magic here, and we can pass it the annotate option. And when we use this, this is what is going to be produced. So here with yellow lines, we see the boundary of the Python code interaction.
Since it's not related to
so you see here,
we
have an interaction between Python and
so
C.
it could,
There's a lot of C code that is automatically being produced here. And you can see here again, we have an interaction because we are using the random from the Python library. And then we return also a value that we didn't specify the type for. So again, here we have an interaction. Also, notice the difference here. I had to put cdef in all my variables here, while this is a more convenient way to specify it if you have many variable declarations or definitions. You provide cdef once, and you put a colon, and then you declare everything underneath. So let's time it. So again, about 0.4 seconds. So any question up to now? See. Okay. So I hope this was clear. No questions yet? Okay, so let's go on. So we saw this very simple thing that we specify with cdef what type our variables are. And now we are going to use another, we are going to see another use of cdef. So Cython offers 3 types of function. In general here, you saw that I didn't specify anything. I just put def here, which is the same as with Python. But apart from def, Cython provides 2 other types of functions. So function declared with def can be called both from Python and Cython code. But then we have the functions declared with cdef, which is the same as the one that we are using for our variables. And these functions can only be called from within another part of the Cython code. So they are not accessible from pure Python. And then we have cpdef, which is a combination of the above 2. So Cython will create 2 versions of the function for you. And with the same name, you don't have to do anything. The difference here is that when you use this function from within Cython code, then Cython is clever enough to call the optimized C version for you, the cdef version more or less. And when you use it from Python code, it will use the def version of it so that you can use it like an ordinary Python function. So we are going to see an example here. So I have my cube function here, which is more or less raises double to the 3rd power. So you see, I say cdef, and now I can specify also the return type. It's the same way we did for the variables. So I have a cdef function which returns a double and just cubes my floating point double precision x that I'm going to provide. And then I have a cpdef function which I call here cube sum. So which it accepts 2 double values, and it will return the sum of the cubes of these numbers. So let's compile this, and I will insert here. So okay, here. So now I can call the cube sum function. It will return the sum cube for this. I can call this function like an ordinary Python function because it was defined with cpdef. If I try to call the other one though, the cube, it will tell me that it's not defined. This function was defined as cdef. So it's only accessible from another part of Cython code. So you see here, I could access it, but from pure Python, I cannot access the function. I could call it cpdef, and then I could call it. In this case, with a cpdef, from within the Cython code, Cython would call the C version of this cube function, while when I call it from a Python context, it will call the def version of the cube. So you see here that now it's accessible. Any questions? Okay, I'm seeing a question coming now. Okay, let me say also this, and then I will share the question. Ah, it's already. Yes, variables are always cdef. So the question is whether the variables are always cdef. So you see that these functions are cdef because they're used within a Cython context, more or less. So it's not something that is going to be accessible from outside the function. So here you can they are declared as cdef. Also, for those of you who are who know C, how to choose when to use. Okay, so the question is how to choose when to use cdef and when cpdef for function. So this is really a question of whether you are going to use this function from outside Cython, or it's going to be called from another Cython function only from within the C context. So if you are planning to use it also from, you want to call this function from Python, then it should be cpdef. So the other question is to tell the code to use Cython instead of Python. We just include Cython in front. So this is only from within the Jupyter notebook. We will see after how you do this outside from the Jupyter notebook. So this is just the Jupyter way to tell it that all this is going to be compiled with Cython. But if you're outside the Jupyter notebook, you do it with a different way. We'll see it after. So for those of you who are familiar with C, there is also the cdef inline, which can be used for sort functions, for example, to you can use this cdef inline. So this function will be inlined, and instead of calling the function, the Cython, the Python, the C compiler will use directly the code of the function when it sees a call of this function. So I just added it here for your convenience, and you can see the annotation here. And there are all these Python code, C code produced from Cython. So another question is, if variables are declared as cpdef, is there a downgrade of performance? I don't think you can declare variables as cpdef because they are already inside the Cython context. See, so if I can do this, so you see, you can, but they are not different. It tells you that it's more or less like using cdef. So it will also be removed. It will not be supported in the next major version of Cython. So inside the function, they have any difference. It's only on what type of a function you declare, like if it's cdef or cpdef. Okay. So from within the Cython world, you can access and use NumPy arrays by using memory views. So you see here, this is how we declare that this is a memory view, a one-dimensional memory view. You see a vector more or less. So you can access the NumPy, the memory views methods more or less here. You see that I specify I and N is the shape and 0 here because it's the shape, the first dimension of the array, which is more or less its length, and I can access it here. So I don't need to pass an extra argument that is the length of the array. So now I will just do the summing of this array, and you see here there is a slight interaction with Python, and we will see why. And then I return the sum. So I can check whether the sum is the same. Of course it is, by using the NumPy method and then using my sum. So you can pass NumPy arrays directly in Cython functions. And this holds true also for two-dimensional arrays and three-dimensional arrays. So I have here my sum to D, and here I get the rows and the columns, which are the shape 0 and shape 1. And I do a double loop. And again, here I just sum, and of course I get the same. Any questions? So progressively, we move from the Python world to C, to the C domain, by using more and more information and supplying more and more information to Cython so that it produces optimized code for us. So you see here that although I know S is a double and X is also a double array, more or less a double memory view, I still have some Python interaction with a slight yellow color here. So the deeper the yellow color, the more Python interaction we have in our code. So here we don't have that much interaction, but we can completely eliminate the Python interaction here. So whenever we have, whenever we use indexes with arrays or memory views, it's the same thing. For our safety, Cython does it checks that the indexes of the arrays are within our the length, the shape of the array, so that we don't try to access something that is outside of the memory that is allocated for this array. And also, although in C this is not possible, because we are using more or less Cython, which supports the Python syntax, we could use negative indexing as well. And this is what the wraparound is about. You can use negative indexes to access elements of the array, which is a really convenient way to access them. But in our simple sum example here, it was really trivial to realize that we are not going to go outside of the bounds of the arrays, because we took the rows and the columns from the actual shape of the array. So we only go from a range from the rows and the range from the columns. So we are sure that we're not going to go outside the boundaries of our array. So we can see import here. This is the Cython way of importing things that are going to be used from within a Cython function, the wraparound and the bound check. And by decorating, this is the decorator, that it goes above the function definition. So by decorating our function with wraparound false and bounds check false, we instruct Cython to disable this checking of the indexes and the wraparound check. So this is more efficient because it eliminates all this checking every time we ask for a particular index of the array. So if I now compile this, you see that here we no longer have any Python interaction. And by checking into that, you can see that it's just 3 lines of C code here, while in our previous case, you see here that there's an if-else block, 2 else-if blocks more or less, that check that we are within the boundaries of our array. So by eliminating this check, we can make our code even more efficient. So any question up to now? Is everything clear? There is one question coming. I'm waiting for the question. In the meanwhile, we are going now to see how we can release the GIL and parallelize loops with Cython. So the question is if it is possible to write actual C++ function like std accumulate. So I have an example in the next notebook, and also in some in the other way that I'm going to show you how to compile Cython code from outside the Jupyter notebook, that shows you how you can actually call either C or C++ code. And in fact, we will see that from within Cython, you can access standard library utilities and collections from the C++ standard library. So let's go to something more fancy now and a little bit more color with color. So here I have the function that will let us calculate the Julia set using Cython. So for those of you who are not familiar with this calculation, I'm just going to show you how it looks like here, so that I have a picture to show you. So by calculating the Julia set, more or less, we see for all the numbers in the complex domain, by repeatedly applying computation, how quickly or how slowly, or if not at all, a certain complex number, if we raise this to some powers, this its absolute value goes out, its magnitude goes out of some certain boundaries that we specify. So I use this example because it's very trivial to parallelize, because we are going to apply the computation for each complex number that we want, and each complex number computation is completely independent from the other ones. So I have here more or less my function. It accepts two arrays, which are the x and the y coordinates of the points of the complex plane. So more or less it's the real and imaginary part. Then we have cx and cy, which are some constants which we are going to use and more or less specify the kind of relation that we are going to use for this iterative computation. And by changing this can be changed here. You see, I specify 1c, and it's the real part and the imaginary part of this. And by changing these numbers here, the picture will change. So I put some number here that I know that produces some kind of nice picture. And then we have the number of iterations that we want our loop to do. We have the radius, and this is the radius squared, which is easier to check because we don't have to apply square roots, whether the magnitude of the squared magnitude of our complex number has gone out, has exploded and gone out of the radius. And here we are going to return the array, which is an integer, and more or less it's a number which tells us at which iteration our complex number exploded. So more or less we loop for all the rows and columns of our arrays, and we do this iterative computation and always check whether the next computation made our complex value to go outside of the radius. So compile this. So here I use the mesh grid function from Numpy to create a grid of points in the y and the x direction. So we get two-dimensional arrays where the one contains the x coordinates and the other one the y coordinates of the complex number that we want to calculate. And here I added some stuff so that we can plot this with matplotlib. So I can change this with something else, and you will see that this will produce a different picture. Also, the time that it takes to do the computation is different when we change variables, because there might be more iterations needed for some of the pixels to explode. So let's try something positive. So this went faster. So you can do some experiments on your own. So here also, for those of you who are familiar with C, I can specify const to my variables, because I tell this way Cython that I'm not going to change this argument within my function computation. So here, just one thing to take into account. When I pass memory views here in the Cython function, more or less, I just pass a pointer to this. It doesn't copy the whole array. So when I make a change to the array, this is going to be reflected to the array that I pass from outside the function. And this is why I can return also here my Julia array. So I create the values of the arrays here, and then I return it via the function. So I have to pass it as an argument here. Any question? So this is trivial. If you don't understand completely the computation, it's just some computation so that you have some, so that the CPU has some work to do, which is very easy to parallelize, and it also has some color. And now we're going to see how we can parallelize this computation. So I said that this computation is very easy to parallelize because every time, every pixel, every complex number in this complex domain that we are going to do the calculation for is independent for the other. So we can use all our CPU cores to do the work for us. So each core will get assigned a different complex number, and then it will calculate the Julia number, the number of iterations required for that number for us. To do that, I can use the p-range that Cython provides, and I import it via from Cython.parallel C import p-range. Again, you see here that I use C import for the p-range function because this is a Cython thing. C import p-range, and I changed my p-range, my range to p-range. So I make the outer loop parallel here. And just one thing to notice, as Raphael said in the morning, the Python interpreter has the global interpreter log. So this does not allow many threads in the same Python process to run at the same time. But from within the C domain, and Cython allows us to do that, we can release the GIL because there we are running without the limitations of Python. So p-range accepts another parameter here, which is no GIL, and I say to it that I don't want the global interpreter log to apply for this p-range. So let's compile this now. Sorry. Let me change so that we have the same numbers here. So here the computation took 0.7 seconds. And here, by the way, Cython will use OpenMP from within C to parallelize this p-range computation. It will use a for loop with the Pragma MP parallel underneath. So I compile again and I'll run exactly the same time as before. 7:55, 7:55 again. Let's run. Now it was slightly faster here. But what happened? Because we put our p-range, we told it to release the GIL, but we get the same time. So I just put these things here so that you cannot scroll very quickly and see the solution to that. The reason is that we didn't specify the C compiler, the actual flags that are needed for the OpenMP to be enabled for Cython. So I right here, we forgot to put the correct compilation and linking options. So these ones, although they look like comments, when they begin with the comment here, the sharp and the dis2tils, these are passed via the dis2til packaging utility that Python has. And I tell it that I want these extra arguments to be passed to my compiler. So you see here, F OpenMP. This you can ignore. It's just another compilation flag that you can add. I can delete completely. but it was just there to tell you that this is not applicable only for OpenMP. You can pass more C compiler flags. And then I pass also extra link flags because we need to link also against OpenMP. So now I compile this with OpenMP support. Code is compiled, and let's see. So now I went from 750 to 210 milliseconds. Let me run again. 210 milliseconds. So it's about 3 times faster. So again, I used prange. I told it to release the GIL, and I have to pass these flags. Let me pass also this. Don't think it will make a difference, but yeah. Yeah, a slight difference. So you can pass other optimization flags as well if you are aware of your compiler and the flags that you need. So 258 milliseconds. So we took advantage of our course, but we see how we can do even better. If you have any questions, let me know. Yes, no other question. So how can we do even better? So I told you that prange is going to use OpenMP underneath. Cython will add the compiler directives for you for OpenMP when it sees the prange. So there are other parameters that we can add, like the schedule that we want OpenMP to use. And here I passed schedule static, and I changed it to Julia set Cython static here. And this means that each thread is going to get equal amount of work, more or less. And I specified chunk size of 1. So this means that we are going to tell the OpenMP to arrange this computation by assigning row by row to its or column by column, depending on our computation, to each thread. So you can play with these 2 parameters and see the different choices that you have for schedule and for chunk sizes. And depending on the computation that you have to do, you may have to tweak them to get the best performance. So here we just put our schedule to static and my chunk size to 1. And to be fair, I will call this function, the static scheduled one and the other one with the same parameters to see which one is faster. So the one took 258 seconds, and with the static scheduling, we went to 77 milliseconds, 258 seconds, milliseconds, sorry, and 77 milliseconds. So you see that we can tweak it even more, and now we have more or less a 10x speed up from what we have had before. So we started for 754 milliseconds, and now we ended up with 77 milliseconds. Let me run again. Yeah, pretty consistent. So another schedule would be, for example, dynamic. Just put it here. So you have to play a little bit to see what works best for your example. So here I can even get better times, 70, and we can change the chunk size. So you can tweak even more if needed. Just change. There's also the guided, but I don't want to go more into details of on the schedule because it depends on the actual computation that you want to execute. So you see, this was now worse. So let's leave it static. Chunk size 1. Okay. So let me see if you have any questions. Otherwise, we can move on to the next notebook to see some more capabilities that Cython provides. Okay, so for your information, we can do also the next notebook, and then we can have a short break at 2:30, and then I can continue to show you how you go compiling your Cython code outside a Jupyter Notebook environment, and then how you can wrap C or C++ libraries. So the question is, when should we use Cython and when Numpy functions instead? So as we will see also tomorrow, there are other ways, simpler ways to get close to native performance other than Cython. So when you can use Numpy functions, use them because they're more convenient. You don't have to go by hand on the C domain. Cython is more complicated, is for more complicated computations, like something that you cannot get with a simple vectorized computation with Numpy. And also, it's much better when you want to wrap a library that is already available in C and you want to use from Python. So if you search online, or you probably already used libraries like MPI for Py, HDF5 for Python, most of these libraries that go with this naming convention, like for Python, will use some Cython interface in between to close the gap between the C code and the Python, so that you can call the Python code from within the C code like it was a Cython code, Python library, but getting the native performance. So according to my opinion, Cython is much better when you want to wrap something that is already there, because now there are better alternatives if you want just to accelerate a simple function. You don't have to use Cython for that. Okay, I hope this covered your question. So we will see also tomorrow, for example, that with Numba, just with a simple Python decoration of your Python function, you don't have to go and specify by yourself explicitly what type of arguments you have, what type of variables. Numba will find this for you. And also you have even more, the code is much clearer because you don't change anything. But when you want to wrap something that already is available on C and C++, then Cython is a very good library to do that. Okay, so let me close Cython 1 now. Shut down kernel for this and open Cython 2. Make sure, again, to use this, the correct kernel. So you saw before that I first opened a blank notebook using the Python kernel, and then the next one I chose to opened with the same kernel. Now that I didn't have any kernel already running, it started with the default one. So you have to change it to the one that we have provided for the course. Okay. So let's start. Automatic type interference using Cython infer types. So let's load again our typical libraries here, Numpy, random, and Cython. And again, to be able to use the Cython magic from within Jupyter, we have to use the loadx Cython. Okay. I ran twice, so it told me that it's already loaded. So this is just a warning, don't worry. So this is a shorter way to say annotate my code with Cython. Instead of writing the whole annotate, it's just does A. Now I specify my random, I cdef double my rand, and it just returns the random from Python. You see here that this is cdef, so I can only call my rand from within another Cython function. And now I do the same calculation using Monte Carlo for pi. But now I don't bother doing anything with cdef. I say that this is cbdef, and I decorate with this with infer types, which I see imported from Cython. Infer types true. So this now, I just annotated this for you. It went and found out which are the types of my variables and what the function returns without me having to specify that. So let me run. So you see that we get the good performance that we had before, even though I didn't specify cdef just here. So with infer types, it finds out by itself which type the variables are. So here it will understand that this is an integer variable because I initialized it with an integer value. And then from here, it will understand that x and y are double values because this is what my rand returns here. And from this computation here, it understands that it's going to return a double value. So this is for you to save some typing and let Cython do the work for you instead of going and defining all the using the cdef and giving explicitly the types for each of the variables that you're going to use. Anyone? Any question? I guess this was very simple. This is just a convenience function so that Cython makes the automatic type inference for you. Now, I start talking about extension types. Python is an object oriented language. For those of you who are familiar with classes, this is just a very simple rectangle class. It has two fields, x and y, which are the sides of the rectangle. And the area is a method here, which is more or less x times y, and it returns the area of the rectangle. And then we'll have its perimeter, which is 2 times the summation of the two sides. So this is fine. This is how you define class in Python. Now, you can do the same in Cython, create an object, but the differences here are these. Here we have a CDef class, and I call it CyRectangle. And I specify directly which are my fields here, double X and double Y. And instead of init, now I have the C init. You see, X, I give the values X and Y, self X, self Y, and I have two cpdef methods which do the same as before. But now this is a Cython class. And I can create it like I would create a Python rectangle. Now I have a CyRectangle and call its methods here, area and perimeter. Also, let me create a Python rectangle here. Fine. I can do the same for B. And let's see now. I can print. Now, if I ask for AX, for BX, it was fine, not complain. But for AX, it tells me that object has no attribute X. And this is because it was defined as CDef. So this will be visible only from within a Cython domain. So I cannot use this. This I can use. This is not accessible from Python. And this would be the same if, for example, I have my area here and I try to do this. You see, area now is a CDef function, so I cannot use it from Python. I could only use it from another Cython function or another Cython class. Any questions? So this is how you create classes using Cython, the equivalent of the Python class. Now let's go to something more advanced, not that much, but here I create a class CyRectangles, which more or less I initialize as by giving the number of rectangles that I want, and this creates more or less a number of a list of rectangles, and it populates the list with random rectangles, and then I can get the total area from that. So here you see I have a list. I say list rectangles, and then I can use the Python syntax for a list, although this is a Cython list. So self rectangles, and then I can use the append method that's created. So now it shows me some warnings because I have used a unsigned int here. So it tells me that I'm trying to compare between unsigned and int. So this is just a warning. And now I can create a list of rectangles, a random list of rectangles here. And I can get the total area for this. So let's see if I define a method like that. I define these cpdef rectangles and it returns a list. And I create the rectangles. Here doesn't like something. I get it. Yeah, we'll see after that why this is the case. So this, it doesn't allow me to return it more or less, but we'll see how later, how we can access the list from the outside. So you see this was a Cython list, and you will see the equivalent how we can access it from Python in a while. Okay, so just forget about this. So here we created a list of rectangles and we get the total area directly. For those of you who are C programmers, you can see that you can go even further and even C import from libc stdlib from the standard C library, the classical malloc and free functions. And here I have a sci-range vector, and which is a range with all the values from start to an end, more or less. And here I have a pointer. For those of you who are not familiar with C, just bear with me. Don't care too much about this, but I just added it here so that C developers can see what we can do from within Cython. So I have a pointer to an integer here and an integer value. Then I have a C init, and then I can use a C-like malloc to allocate my data. And you see here, this is the way that the Cython way of doing casting of one type to another. So here I allocate so many bytes as the size of the range vector I want times the size of int. And this is, for those of you who are familiar with C, this is the way that you would do it in C. So now I populate this data using the array syntax here. And now I can use the getItem magic dunder method from Python to access the elements of the range. So here I make check that the index is within the range that I want, and I return the data I want. And here is the destructor, more or less, which calls free of this self data. So now I can use this as a normal Python object and use it with the indexing syntax of Python. I use 2, and it gives me the third value of this sci-range vector. Any question? I hope you have a question here for those of you who are familiar with C. Was it clear up to now? So you see that you can even access the standard C library from within Cython and do even more complicated stuff. Okay, so now to answer also the question that Jose had before, no, Nilesh had before, how you could use, for example, C++ functions from within Cython and call it like a Python function. Let's see how you can access the standard template library from C++. So one thing that you have to remember here, since you want to switch from C to C++, you have to inform Cython that this is the case. Therefore, here you see that these two tildes, again, this is not a comment. It's going to be taken into account by Cython. And I tell it that now I don't want you to produce C code. I want you to produce C++ code because I want to use this functionality from the standard template library of C++. So here I tell it now that from libc++ vector, this is the vector container from the standard template library, and I tell it to C import vector. So I will create again the sci range vector, but I will now let the C++ standard library do the allocation for me. So I tell it that now my data is a vector that contains integer values. This is the way that you would write it in Cython. I have the C in it. And now I use the pushback method of this vector to push values to it. So it's equivalent to what you would use from within C++. You use the pushback to add values to the vector. And now I return the self data, and this is again with the indexing. Again, can access as a vector. And now this takes into account the allocation itself because of the way that that C++ works. This will call the vector distractor when this object is distracted. So I don't need to do the deallocation manually like the previous case. And to go even further, now this is where it gets even more interesting. Before you saw that I was not able to access directly what I was trying to add to return the list outside. But here I can specify to a function. I use a function now, a sci range, well, start and end. I will tell that this returns a vector of integer. I will create a vector and return it. So now I will create this and I will use the sci range like that, and I will assign it to a Python variable. So here I printed the type of X, and you see that it's a class list, and Python printed the list for me. So the collections from the standard library of C++ are compatible with the collections that that Python provides, and Cython makes this possible for you. So the vector int is compatible with the list of Python. So it is converted to a list for you so that you can use it outside of Cython. And the same goes with maps, for example, unordered maps that the standard C++ library has. Cython will make the conversion to a Python dictionary for you. So this is very convenient when you want to use something that you have written in C++, because Cython will make it interoperable with what you are used to do in Python. So now I can use like the typical methods and the typical function of Python with the X that came from C++. So I have x0, for example, 1, sum it. To get a number of different values for it. So it works like it was a Python list from the beginning. So this completes also the second Cython notebook that I have prepared for you. Any questions up to now? Ask me whatever question you have from Cython up to now, and then we can have the break, and then we will continue by showing you how you can compile outside the Jupyter notebook, and then how you can wrap C or C++ libraries using Cython. Okay, so I see that there is a question being typed at the moment. So are all variables are passed by reference by default? So in our case here, for example, the variable was an integer, so this was passed by copying the value. But when we talk about memory views, for example, this is going to be passed by reference, more or less. So here, in the first case that we had for the Julia set, I passed a zero array which was populated within the Cython function. So here we changed the values of the array, and the changes were reflected outside. So the memory views are passed by reference, more or less. And if you want to pass explicitly by reference, you can pass a pointer to it. So you can specify pointers like you would specify in native C. So you can explicitly say that you can pass a pointer. So by reference, okay, I understand what you mean now. So I don't know if this is supported. It could be supported. Let's see. It seems it is supported. Let me try to change, for example, and pass it like that. And for example, here say start equals 100. Assignment reference, no. So yeah, you can pass by reference, more or less. Yeah, what I was trying to do was to say something like that. Yeah, so now it doesn't like this. So yes, it seems that you can pass by reference, but again, I'm not really convinced. I need to check it, and I can tell you after the break. Any other question? Okay, then I think we can do the break now and return at 2:35. Yeah, at 2:35 for the rest. If in the meanwhile, if you have more questions, please type them. So see you in 2:35. Okay, so we can start again. Now, as promised, I show you how we can do things outside the ease of Jupyter Notebook, how we can compile our Cython code without using the Cython magic that Jupyter Notebook provides. It's a little bit, a little bit more complicated than the ease of Jupyter Notebook. So that's why I wanted to begin with that, so that you are familiar with the syntax and the peculiarities of Cython at first, and then we can go and see how you can do things outside Jupyter. So again, do you have any questions from before related to Cython? Also, I looked online and it seems that yes, you can use you can pass by reference by specifying the ampersand syntax. Okay, then since it seems there are no questions, let's go now to Cython outside notebooks. So if you were in notebooks, you can click here, Cython, and let's go to wrapping C. So a little bit here. Okay, hope you can see this. Okay, so these are the source code files that we are going to use. And you see here that there are various files. Here we have our C code, which is prime C and prime H, prime C and prime H. So we want more or less to assume that we have already a library that contains some C functions, and we have the header file, which more or less has the interface for the functions or the function that we want to use. In my case, it's just a function that, given an integer number, it returns you a Boolean that whether this number that you supplied is prime or not. And here is the interface file, the header file, and here is the actual implementation of the function. So I check, this is just an optimization here, whether if the number is either 1 or 3, we return true. If it's 2, of course, it's false. And then we do a for loop and see whether from 2 up to the square root of the ceiling of the square root of this number, we can find a number that divides this. And if we cannot find such a number, this means that it's prime and we return true. This is the function that we want to wrap again. This is the header file. So this more or less has just the function signature that tells us how this function is called, what it expects and what as an argument and what it returns. Now, how I can use this function from Cython. First, I have to create my primes pxd. Here I give the name that I want, but this file has to be created, and it's the equivalent interface file, header file, more or less, but in the Cython realm. So here you see that I specify that cdef extern from primes h, this is the syntax. So more or less I tell it that the function that I want to use is coming from the C word, it's external to Cython. It's a cdef function. And this is more or less its signature. So in Cython, in Cython words, it's called is prime. It gets an integer, and this is the Boolean equivalent in Cython, the bint. So more or less, this is just a copy, a translation of. Let me put it here and have my primes here. So you can see this is the function that is defined outside. And this is the translation of the function signature in Cython words, more or less. So you see, I say that my function is defined externally, and this is the interface. And this is the glue code that will allow us to use this is prime from Cython. Now I have my primes peaks. And now, in order to be able to call this function from the outside, because it's a C function, I create a wrapper function which more or less calls the is prime. So I cannot directly call the is prime because it's a cdef function, but I have to create a wrapper function around it, which is cpdef. So I call it here implementation is prime, which calls the cdef is prime that is defined here. So now this function I can use as if it was a standard Python function from an example like this. And I say, from my primes, which is the pix file, import imp is prime. And I say numpy, and then I use a list comprehension here, and I will execute this script, and it will return the 10 largest primes between 100,000 and 1 million. So this is my Python script. Now, this was a little bit more complicated, of course, than having the code inside the Jupyter notebook. And the more complicated is yet to come, because here I have the setup script that we need to create in order to compile this code to be used by Python. So this is the setup script. Let me delete the other ones. So this is some boilerplate. The important here is the Cythonize. So from Cython build import Cythonize. So I tell Python that my extension is called my primes, and that the source code for this is the pigs file and the primes C. So not the header file and the pxt files, the pigs and the primes C. And then I say set up, the name is my prime, and the external modules the extension modules that it has to be created is by using Cythonize, this extension, and I pass the compiler directives that I want Cython to use the syntax for Python 3. So I put all this here so that you can use you can see also how I can specify this option. So I have a README here, how you could compile this, and let's go and compile it. I will open new terminal now. Where is it? New terminal. Let me see. Close this. Let's go. New terminal doesn't open for some reason. New terminal, but we could know why it doesn't open correctly. Refresh it. No, we can do yeah, here it is. Here are the terminals. Close them first. Expression. So while it refreshes, let's have a okay. Okay, so you might see some slow down on Jupyter. Yeah. So in the meanwhile, I can move to a normal terminal to show you how it looks like. Okay. So let me move to a normal terminal because Jupyter is taking some time. So, okay. Can you see my terminal? Okay. Is it visible? Should I make it larger? Okay. Okay, so if you see here my README, I say that I have to execute this. So set up Py, build ext in place. So let me copy this. Sorry, I have, for me it's Python 3 locally. So it does all these commands for you. So here it called the C compiler with many flags, which you can change, as we learned with the these2tils comments for bypassing from the setup script. And now, if you see, it has created a myprimes.so file. Is it visible? Is it? Okay, so it's visible. So this is more or less the dynamic library that it created for us. And this is what I can use now from within Python. So now I can say Python print primes, and this is going to execute. Will use the library from the Python library from the .so file that we have, and it will execute. Also, we could see it in an IPython notebook, for example, that I can do from my primes. You see, even with tab completion, it realizes that this is compatible with Python import. Imp is prime. So I can say is prime, 10, for example, false, 11, true. So now I can call this function that was written in C like a normal Python function. But remember now that since it was compiled using C, we will get the native speed of the library as it was all in C. So any questions? Let's see it one more time so that you understand. So I have my prime. So here is actually the my primes C is what was created by Cython for us. So it's a really long. It's a huge file, but it's what Cython generates for us. So it's not meant to be easily readable, but you can understand if you look at the actual, if you remove the actual, if you don't look at the actual boilerplate code that Cython puts for you, that Cython generates for you, you can understand if you're familiar with C what is happening. So let's see, again, we had my primes 8, my primes pxt. So you can see here, we had this function signature in C is prime. We create the pxd, which is more or less the glue interface from within Cython to C. So I specify that I want to, this is externally defined in C, and it's called is prime, and this is the signature that I can use from Cython. And then we had my primes pix. No, bin. Yeah. So this is my primes pix, where I call is prime, which is a cdef function. And then this is my wrapper function that I can call now from within Python. And here in print primes, I import from my module, like it was a normal Python module, the imp is prime, and I call it naturally. So there is a question that says, do we always need all these types of files, C, H, PIX? whenever we use Cython outside of notebook. So in our case here, we needed this because we had something already written in C and we wanted to wrap it and call it from Cython. But if we have something that is written, typically Cython code goes in PICS files. So if we had a Cython function like the ones we defined in the notebook itself, we could have only the PICS file, then tell it to Cythonize it, and we could use it directly. But if we want to wrap an already defined function in C, we have to do this, yes. So here it was not only a matter of notebook, it was also a matter of having something that is already written in pure C, not in Cython. So to give you an idea how, okay, it seems that now the Jupyter Lab is back, but since it doesn't make a difference, let's continue here on my. So we could have, for example, copy my primes peaks. We could have a primes peaks, and we could have like CP dev. Being is prime like that, and here and we could make it like this in pure Cython. Okay, so then we would have to write it in Python and a Cython way. Okay. So I turn it all to Cython syntax. So now this is what we would have written in the notebook, for example. And now this is a PICS. So I could do Cythonize. Oh, yeah, of course, this is not valid Cython. So here I told it to Cythonize in place. This is my primes. So here I wrote, I didn't have previously defined C function. I had something that was Cython. This is what we would put inside the Jupyter notebook. So here we don't need any PXT or H files or whatever. We just do Cythonize in place and with Python 3 syntax, primes.pix. And now if I go in Python, for example, I can say from primes import is prime. Okay, so now I imported like a normal module. And you see here, it has created the same name as the pics that I created here. So more or less, this is what we did in the notebook. We didn't write a pure C code so that we should wrap it after. We write pure Cython. So in terms of the notebook, we did the Cythonization. So is this clear? Okay. So I can add this to the notes if you want, but it's not something really critical. I will show you the Cythonize command also in the other example to wrap C++, but it's just a different example. When you want to wrap, you have to create this pxd file and then the pics to create this like interface between the native world and the Cython and then Python world. So you need all this stuff. Now, let me go to wrapping C++. We have a C++ here code. So here, I'm going to use something that is already in the standard C++ library. So there's no need to have a header file because it's already something that is available in C++. Maybe let me see if I can turn to the Jupyter notebook because it will be clearer. Let me see. Okay, yeah, so now, is it clear now? Okay, so I'm going to wrapping C++. And now we don't have a setup script because now I will show you the Cythonize command. And I want to create a PyMC. It's like we used before, but now I want to use the random number generator that is available in the standard library from C++ 11 and afterward. So here, now the header file is already included because it's included in the C++ standard library. But again, we have to create the interface file, which is the pxd thing. So if you go to the pxd file, I tell it now that I want cdefx from, now this is the random header from the C++ standard library. And I tell it also that I want to import from the standard namespace. And now I want to wrap, to interface more or less Python classes, standard C++ classes. So I say, this is the class that I want. This is called MT19937. It's a Mersenne twister random number engine. And then I have also a uniform real distribution, which is a template class from the C++ random standard library. And I tell it, notice here that I only specify, because there are many things inside this class, I only specify the things that I am going to actually use from within Cython. So in this case, I only need the constructor, which accepts a seed for the Mersenne twister engine. And then I only need the real distribution, which accepts this, and the operator from the real distribution that accepts the generator, the Mersenne twister generator, so that I can get my uniform random number. And then in the pics, I have again a cpdef where I will calculate Pi using Monte Carlo method. I have my cdefs here, in circle, my for loop counter that I will use here, I, x, y, and then you see here, I create an instance of the Mersenne twisted generator, which I imported from the empty random, which was the pxd. So from there, I see import the Mersenne twisted and the uniform real distribution. And now I create a uniform real distribution with a template of double, and I give from 0 to 1. And here I call this distribution by passing the generator. To understand what is happening, this is the operator that I'm using. You call the object instance like a function, and you pass it the generator. So this I can use because I included it in the interface file, the pxd file. So it's accessible for me from within Cython. Also this, you see, this was accessible for me here because I included it in the interface. And again, the empty 19937 accepting a seed was also available for me because I included it in the interface, and I used it here to create an instance of the Mersenne twister. And the end thing is that I have a Pi calculator which just calls this PyMC with the number that I give it, and it calculates this for me. So now I have the README where I say Cythonize like I had before. So if I open a terminal, I can now tell it to Cythonize for me. No, it's in Scratch. Let me see. Can I open a terminal here? Yeah, okay. So let me open a notebook, and I will do it from within here. So you can run shell commands from within the notebook. Let me close the others. So I have an untitled notebook here with my kernel. And if I do this, I tell it with an exclamation mark, I tell it to run this on the shell. So this will not run in Python, but on the bash shell. So I Cythonize. You see here that it gives me everything that I would have on my terminal. One thing also to be careful of. I told you above that before that I have to pass all this stuff explicitly inside here, and I want C++ language. And now, because I need C++ 11 and beyond to be able to access the random standard library from C++, I have to pass also that I want the compiler to use this option for the compilation, and I don't think it's needed for the link args, but I just added it here. So that the standard is C++ 11. So if we go here, you see that it has used this option for me, the C++ 11. Okay, so now I can use Python, my calculator. Again, now I will use the shell, but I will call Python this time. Python, my calculator with 100 points. Of course, it's not a good approximation. Let's put more. Yeah, we put a lot more. So this used the Python script, which called a Cython function, which by it on itself wrapped it used a random number generator that we got from the standard C++ library that comes with C++ 11. So you see here, again, the same procedure, but now we don't have the C code or the C++ code that this here was generated by Cython. In the beginning, we only had the pxd and the pix file. We didn't have the C++ code in the header file because these are coming from the standard library of C++. So we just use Cythonize and we are ready to go. Questions, please. One thing that I forgot to mention before from the second notebook is that I have a link here in the final line of the notebook. You can open the definition files that it will take you to the GitHub repo of Cython, and you can see which utilities from the standard library of C++ are available, so that you can use directly, like I used the random number generator. So that was it from my side. Any question? Feel free also to ask questions regarding Cython also tomorrow or the next days, because you might work a little bit by yourself and see that you come up with some question that didn't come to you when you were watching the lecture, but by posting it on Slack, we will be happy to answer it to you. Also, there is the Cythonize command does all the good stuff for us. Like it first uses Cython to generate the C++ code for us, and then it calls the compiler. There is also the bare Cython command that does the first step, but Cythonizing or using a setup script is more convenient because it does all these steps for you. So you saw here that the actual Cython command created created the C++ file for us, and then it compiled that. So this was the file that it generated at first. In C++, you can see it here. And you see here that these are what we have passed, and it populated it with some more stuff. And it has all the source code. So you can either use Cythonize or use Cython and then call the compiler with the correct flags yourself. So was everything clear up to now? Let me write. Okay, so for those of you who are not familiar with C and C++, don't worry, because tomorrow we will see another way of being able to run with native performance without you having to be a C or C++ developer. So that's why my first reply to the question whether to use Cython or not was like, there are better solutions now if you just want to accelerate one critical function that takes most of the time in your code. But Cython gives you all this control, what to wrap, what to interface, and what not. So you can wrap some libraries that you already have developed in C or C++, or you can use some functionality from the standard library of C++ that you're already familiar with, but you want to use it in an interactive way with Python from within Jupyter, for example. Okay, I guess that was clear. Should we do a 5-minute break or we should go directly?
I should go directly.
Okay. Okay. So have a nice afternoon from me, and Rafael will continue now with some more stuff, how you can wrap libraries and link with native code.
Okay, thank you, Theo. Good afternoon. So now in this, the remaining of the afternoon, we will have a very short session that we're going to have a look to how to bind into Python Fortran code and C code. And for that, just let me share the screen. So, just a second. Yeah, for that, we are going to have a look to two approaches. One is F2Py. F2Py, I briefly mentioned it early in the morning. F2Py is a program that comes with Numpy, and yeah, it's a helper to write code to help you to bind code from Fortran to Python. And we're going to have a quick example to see a quick example here. And before we go to the notebook, to the tutorial, we are going to use also today for C something called CFFI, which stands for C Foreign Function Interface, and is something similar but for C. And with these two things, even if you don't know C and Fortran, I think my opinion is very convenient to know them, because sometimes there are very small things that they are hard to get a good performance in Python, if or would require a lot of effort to make it running with a good performance. And these things you can write it very easily, even if you don't know too much C, and you can get a very good run times and out of this. And also in the other hand, you can easily call into Python functions and code that already exists from C and Fortran, and that one can be very useful as well. So we're going to come here first to the folder F2Py, and there are a few ways to do this, but pretty much it's different. I'm going to explain you the more basic one that requires the less amount of specification from the Fortran side. And so there is a notebook here, but there is a README file, which is this thing here, that has all the information. And yeah, so here we have So if we go to distance F90 inside of F2Py, we have a few files. So one is our Fortran code. So this one is going to define the CT block implementation in Fortran. So remember in the morning, at the end, we said that for the CT block distance matrix, we cannot apply this nice trick that we apply in Fortran, sorry, in Numpy. And then we can try other solutions beyond Numpy. And this can be one of those. And here, so we have this code in Fortran. We have the same thing for the Euclidean, just for comparison. And we have some code to test it. And just also to show you how to import it. And there is a setup.py that we can use to build the whole thing. So I will go very quickly through it. And so the Fortran code is very simple. If you don't know Fortran, just look at the definition of the function. So CT block distance matrix. We pass the x and y, which is the same thing that we were passing in the morning, a list of arrays. And n samples and n fit are the number of vectors, so the number of samples, and n fit is the number of the dimension of the array. And as a new thing, we are going to pass here, we have to pass here this variable r, that will be the distance matrix, the result. Because in Fortran, these subroutines, they do not return a value. This is not like, it's not a function, it's something different. So the calculation is going to be done, and it's going to populate this r here that we pass as an argument, and then it will change it will populate it, and when we call it from Python, we will define it first, and Fortran is going to write where we define this in the memory of this variable. Okay. So this is some Fortran definitions of that you have to put for the arguments. And here, this is very simple. It's just two for loops that goes through the samples, through the list of vectors, and one internal loop that does the distance. No, this absolute value of the subtractions. And then this is going to be put inside of R, which is the matrix. Okay, so this is very simple. And the code to call it before we build it, the code to run it. I have this one open somewhere else, apparently. Ah, no, sorry, I opened the wrong thing. So the call to open it, to run it. So we import it. This one, you will see afterwards why we import it like this. But it's very simple. So we generate data. So the matrix we're going to, the list of vectors is 12,000 by 50. And we generate random data. And as I said before, for this R here, we need to generate to give an Numpy array. And for that, we create this CBDM, CT block distance matrix F90, and we create this as an empty array. So an empty array is an array that is allocated, but it's not initialized. So the element is going to be whatever it was in the memory when it got initialized. Allocated. Okay. And n samples and samples, n by n, as we did in the morning. But the new thing is that we have to put order equal Fortran, because otherwise Fortran, when writes in this memory, which is what it's going to do here, is going to understand everything as the transpose. Well, actually the opposite. Python is going to understand everything that Fortran wrote as the transpose, because Fortran uses a different ordering in the for to store memory, which is actually the transpose of C, which is what NumPy uses. So we have this empty matrix in Fortran order, and this one you put it once, and for the rest you you work with it as you don't care that is in the background. In the backend, it has a Fortran order. So here we measure time, and we call the function, which is we're calling exactly this, and we pass x transpose, so the data, and we pass transpose because of the same reason. We have to give to Fortran in the shape that is going to the stand, and this is one very good thing of F2Py, which is that even if this initial data that we created here is not in Fortran order, by doing this X transpose from the NumPy side, F2Py is going to tell this function to use it with the index to see it as a transpose. So this function is going to understand it as a transpose, as a Fortran order, so which is a transpose, without having to change data. And this is something very nice. And so we pass the number of samples, number of features that we need for our loops, and the empty matrix. And when running this one, Fortran is going to write in this memory, in the memory of this this variable, and that's it. After this call, this value here is not going to be an empty anymore. It's going to have the result that Fortran calculate. And we also import this thing from Scipy. It's a CDs, it's a city block implementation, that we do it only for comparison. Okay, so now we can leave this one open and check. So all the instructions to build are here in the README. So we're going to use the setup.py, and before having a look, we're just going to build. So we copy this one, paste it here, and yeah, we'll do some stuff. And it takes a long time because you will see now, this F2Py doesn't create a direct binding to Fortran. Instead, it creates wrappers to the code that you gave, and it creates Fortran wrappers to the code that you gave, and then it creates C wrappers to the code that is wrapping the code that you gave. And with Python, Python is going to read this last C code that was created. So it's a long thing. So it ran, and it created this to build, which is a temporary file with some folder with some files inside that he needs. Like for instance, you see this CBDC module is a wrapper, and this one is another wrapper. So if we look here, you see now that there is a longer thing that was generated. That it references our code, and there is also this one. So I open the same thing. That this has a lot of things. This is the C wrapper that is calling the code. And you see these kind of wrappers that they always use this Python.h, which is the Python headers for C. And yeah, and that's it. So it's already built, and this is the final module that we built, metrics. And inside of metrics, we have these two libraries. This is what was created, and that's why we import it like this. So from metrics, we import this name. So from metrics.cbdm, import this one. And yeah, and finally, the last thing, let's see how this thing is built. This is in the setup.py, and this roughly is going to run something like this. F2Py, you can do it by hand if you want. Here's F2Py, you pass the code, the name that you want. This is the name that we use to import, and some flags. But here, if you package or something and you want to distribute code, it's better to do it with a setup.py, as Theo said before. And here we're going to use these utils, similar to what Theo showed before, but now we are going to use this util implementation from NumPy. So we are going to do from NumPy.these utils. Okay? I see there is a question, maybe have a look. My metrics folder is empty after running the rapid command. So if you're following with me, remember that here you have to have the environment. I don't know if that's your case that you have it. So you can go to the general, to the information, and the last thing, you get this last command, and you activate it. Yeah, it shouldn't be empty. All right, that was it. Thanks. Okay, thank you. And yeah, so if we look at the setup.py, we use the NumPy these utils, and we define this thing that is called extension. And extension, it will be each of the Fortran code that we have. For instance, we're going to do two extensions here. One is Euclidean F90, and one for CityBlock F90. And this is very simple. You put the name, it's the name which you're going to import it. So that's why we call it imported like this. And this library you saw is cbdm.something. You pass the sources, flags. So these flags that we're defining here. So this is for the OpenMP directives that we put wrapping the loop. So the language, and F2Py options, we just put verbose. You don't have to put anything. That's why it printed so many things. And that's it. So you can create as many extensions as you need. And at the end, with this setup, you evaluate the whole thing. And here we call the package metrics. That's why we have the metrics folder. And yeah, and the extension modules, ADM and CityBlock. And that's it. So ADM and CityBlock is these two that we put here. And that's it. This is let me see that. Yeah, this is I don't know. It's fairly simple given the amount of work that that it helps you to do. And now we can test it. So we know how to run it, and now we do Python test CityBlock. Ooh. Maybe delete this. I will rebuild. I don't know what happened. Okay, so and here you see the speed. So this is compared to cdist, and for 12,000 by 50, this data that we generated, it does it in yeah, around a bit less than half a second. And we can, oops, I got something here, I think. Yeah, and we can test also our Euclidean distance matrix that we are comparing with the Euclidean trick. Okay, yeah, pretty much the same time. So that's it. This is in the basics of F2Py. I think, yeah, we have a bit of time, so I can show you quickly another way of doing things. This is very similar, but it gives more work to the F2Py side, and I will show now what I meant with that. So this is the one I show you. And so if you are more familiar with Fortran, you can. Yes. Trying to open this. No, it's this is a different way of writing. So now, for instance, no, sorry, yes, I went to the same folder twice. Okay, sorry, that's why I was complaining. So, so there are two different ways of writing, and so this one is like the minimum you can do in the Fortran side. But here in the Fortran side, you can be a bit more explicit in describing the data that is going to be passed. For instance, here, comparing this one to this one line by line, here we said X is of this size, of this shape, and fit and samples. Remember that it's going to come transposed, right? Y the same, and samples and fit doesn't change, and also R. And also we put here that R in this case is going to be the intent of the variable. This is what you're using for, where you're using it for. It's going to be as output, and this one as input. And here we have in-out. So it's going to be something that you will pass, and something that that it will read, and something that it will write and give back. So if you have a more, yeah, like I said, a more better command of the Fortran language, you can do something like this. And now F2Py is going to be, it's going to play smart, and it's going to do cool things like, like this. So now you import it and you build it exactly as I showed before. But now from this information that you gave here, F2Py is going to guess that this function here, all these things and samples and fit and R are named arguments, are optional arguments. So, and it will also guess that the last one, the R, is going to be an output of the function. So it's going to create this Python wrapper that it will automatically generate, give you an output. It will give you the result as normal, I don't know, the normal way that we program on Python, and that's it. The only thing that you need to do is to write a bit more elaborate this part. But yeah, that's it. Then you have the both options. I think that the main point is that even if you know very little of Fortran, F2Py can be of use for you. And this is also that this is a very simple implementation of this function. Probably we can even do better with more smart way of running through the variables, through the elements. But you can see already the very good performance that this thing gives without not too much work. And that's it. I'm going to stop this part here. And now let's have another quick look to CFFI, which is C foreign function interface. Yes, I'm going to do the same thing to look to CFFI. All right. So in CFFI, there are two ways of doing it. So we're going to do something very similar to what we did before, but we're going to start, or at least to have a look to this one, and if we have time to see the other one. We're going to start with this way that I call it code version. So here where I'm going to clean. I didn't clean very well. Okay, here similar to before, there are a few files. I only did it for the CP block, but we have the code, the C code. So and the C code is again the same thing. It's very similar to Fortran in the definition of the function. We pass a, B, which I don't know now why I call it like that, but it's X and Y. A, B are the distance matrix, rows, the number of rows, and the number of columns, the number, the size of our data. The inside is exactly the same, and so just some iteration over iterating over the rows, and then calculating the distance in the central loop. And it will populate R, and it will be the same mechanism as we did before. Here, C is going to be writing in the data buffer of a Python array that we're going to use to store the R. Okay, so that's it. This is the code. Yeah, of course, we add here some OMP directives to parallelize the loop. Yeah, let's go here. Code. We'll leave this one open. And yeah, we also have ctblock.h that we also need. So if you're not familiar with C, this is a header file, and I just simply put the definition, the signature of the function. So it's just the value that it returns, which is nothing, void, and the name and the arguments. That's it. Like this, here we use a script instead of a setup.py. We use a CFFI script to build the code, and we're going to do right now exactly the same that with F2Py. We're going to build it, and CFFI will generate a C library. So C binary that is going to be importable from Python. And again, it's very simple. You import CFFI, and CFFI has this object, capital FFI. So you create it, and then you read, like literally open it and read the content of the header, and you pass it to this ffi.cdef. That's it, just the content of the header. And you do the same thing with the code, but you just put it in a variable. Okay? And then with ffi.setSource, you put the name of the module, how you want to call it from Python. You pass the code, which is a string, and compile arguments. We pass the OpenMPI variables to, command line arguments to activate it and to build with OpenMPI. And then we do FFI compile, and that's it. Here from, if we open the test, we do something similar to what we did before. So this is familiar for you. We imported, this is the name that we gave to the module underscore ctblock. And here it will be inside of .lib always. And so it's something that you have to do, .lib, and it has the name of the C function. Here the same thing, we generate data, we create one of these FFI objects. And before evaluating calling the function, we need to get the data buffer explicitly from the Numpy array, and this is what we do here. So this x.ctypes.data is the data buffer. This is going to be the C memory of the Numpy array. So the gray block that we saw in the morning, that the Numpy array has the data stored. And we're going to explicitly give the corresponding C value, sorry, C type. So we define it as a double pointer to this memory, and we call this XC. So from here, XC. And we have to define the distance matrix as we did before as an empty array, and we also get its data buffer, and we call it RC. Exactly the same thing. Now we measure time, and we call the function, and here now we call very explicitly with the C variables, with this XC and RC. So we have XC, so to A to B. Remember, this is Y and X and Y. I don't know why I call it A and B. And the R, which is what we are going to get the matrix, and the number of samples and the number of dimensions. And that's it. Similar to with Fortran, this thing is going to call the C function that we already have built. I think we haven't built it yet. And the C function is going to write in the data buffer of RC, and it automatically R is to what R is pointing to. So it's going to change the value of R, and that's it. This is how you do it. And this one, a good way to do it, if you want to ship it, you can create wrappers. You can define a function that you pass the user of the function will pass NumPy arrays, and then inside the function will do all this part. That this is not change of memory or anything. It's just a very quick casting of memory, and it will return R. Okay, so and for a user of the function, he will the person will never know that this is a C function. It will behave as a NumPy function. So let's build it. We have built it yet. Yeah. Do Python CFFI city block. That's it, and it will create this thing, this library. And now let's test it. Test city. And that's it. Yeah, very simple. So this is the code version. That the difference I will open here with what we are going to do now. We're going to see now is that we read the content of the header and the content of the C of the code, and we gave it to CFFI to build it into a binary. Now there is another modality of doing it, which is very convenient because what is called here lit version. So here we are going to create a library first, and we are going afterwards with CFFI to tell CFFI to create a wrapper for that library. That means that if you have a C library that you want to call from Python, if you don't have the code, you have only the library, you can create it using this. And the difference is, let's open the CFFI thing. So here we don't have the code, right? So we are going to this part here until here is going to be the same, right? And we read the header, so we have to know what is inside of the code, the signature of the function. Okay, and so we pass in the set source. We write include the header, so this header, and then the rest is the same. And yeah, here we have the name of the library that we want to bind to, and yeah, we can do like this. So I created this make file that does the whole process, But we're going to do first the first part, so which is this one. We're going just to compile. We do grep, make, and this is C. So there is no Python here, and this is going to create a library. This is a library that we're going to create the binder to. And to show you, if we use nm, it will show you all the symbols inside of the library. So if we do grep py, there is nothing in Python. So this one you cannot. This is just a C library you cannot import in Python. But now we do the rest of the thing. So this is what we did, just the C part, and now we run Python CFFI. So we do Python CFFI city block, and it will generate the binding to this library. And now we have this one here. And now if we do the same thing, city block grep py, you will see that this one has a lot of Python symbols inside. This one is a Python importable library that is going to call this library. And now we can run it. But now when we run it, depending on our configuration, we can see this error that it doesn't see this library. And for that, only what you have to do is to add the path where the library is, which for us is the current directory, to the library path. And that's it. So all this is written in a form of a tutorial in the CFFI README. So you can open it as Markdown preview. So, the two versions, code version and library version. Okay, and that's it. This is all I think you need to get started to do bindings to from Python to C code and Fortran code. I think I saw something. No, there is not. That's it. If you have questions or something, you can ask them now, or otherwise any point of the course if you play with this at some point and something is not clear. Otherwise, otherwise I think we can finish here for today. And tomorrow you will be with Theo the whole day, and everything is going to be about Numba, as he announced, and also the rest of the time we'll be working with GPUs. I thank you for your attention and staying the whole day with us. There is something you would like to say? Okay, then we finish here and hope to see you tomorrow at 9. Okay, goodbye.